see, I think we're live. Are we live? Oh, shoot. Oh no. My ear is just falling to the ground. This is tragic. Oh no! Okay. There you go. Alright. Let me. Oh no. Okay. Let me. There you go. Let me take a look at Twitch. Yes, it seems like everything's working fine. Right. I think so. Yay. Alright. This should not be, actually, this should be the Solana white paper in Rust. Perfect. Alright. So, welcome everybody. Welcome to, this day of today. Let me edit the title. There you go. Solana white paper in Rust. So, welcome everybody. I hope you had a good day yesterday and that you're going to have a good day today. So, what are we going to do today? Today we're going to dedicate our time to take a look at the Solana white paper. And then we're going to continue learning Rust as usual. Yeah, that's going to be mainly the plan of today. So the Solana white paper is, if I remember correctly, a little bit longer than the Bitcoin one. So it's probably going to take us 2 days instead. That's completely okay. I do have to go potentially at like 12:30 to lunch with like someone. But yeah, we'll see. Hi, Penguin Operator. Hopefully you're good. And yeah, you'll be back? Okay, I'll see you. So yeah, let's transition here to the coding scene, as usual. And let's try to take a look at the Solana white paper. So, remember, okay, before we start, right, there is a reason why we are taking a look at these specific things, right? So, first one, it's Bitcoin, because Bitcoin started, it was sort of the pioneer. You could also consider BitGold. I'm not very sure of what the differences between them are, because from what we've read of BitGold, it had basically the same system as Bitcoin. Anyways, so Bitcoin is the pioneer, the one that started everything. But Bitcoin has a problem. It has mostly two problems, right? That problem is it's very slow. It's extremely slow. You can only process like, what was it, 6 blocks per hour? Something like that. 6 blocks per hour, with every block having around 4,000 transactions. So then you can imagine, 24,000 transactions sounds like a lot. It really is not, right? Per hour. So, So we have the problem of speed. And Solana was created precisely to solve this problem, which is the reason why we're reading the Solana paper. Because we need to see how the problem of speed was or at least Solana's contribution to solving the problem of speed. We also have a problem with both Bitcoin and Solana, right? So focusing on Bitcoin, which is the one we read, there is a problem with privacy. Like, not so much a problem with privacy. Bitcoin offers very good privacy, and it's not like your data is going to be revealed. But it is, with enough dedication, possible to see or to sort of deduce, right, where transactions are coming from, who the owner of an account is. It is a little bit difficult to hide your tracks. It's relatively possible for blockchain investigators to trace the history of transactions back to a given account, right? So that's what we're going to take a look at. that problem, and that problem is solved by Monero, or Monero at least tries to solve this problem. So we'll take a look at Monero's contributions. For now, those three are the main ones. So Pioneer, speed, privacy. Okay? So this is our speed chapter. Alright. Let's go with it. Let's go with it. So Solana. Yay. Let's take a look. Okay. There you go. Let's see. Just a little bit. That is not symmetrical. Why is it zoomed out like that? Yes, I want it to be symmetric. No. Why is it? Okay, that's fine. Alright, so let's begin our reading. Our usual reading. Hi you jokes. Solana programmer I think is a very nice solution and good choice. Yeah. We'll take a look at it. We'll see what it entails. It is very long. 32 pages. I'm not sure what we're going to be talking about. Given that the Bitcoin white paper was like significantly shorter. But it's okay. Alright. Solana, a new architecture for high performance blockchain. Version 0.8.13. By Anatoly Yakovenko. So Anatoly Yakovenko. It's him. This is Anatoly Yakovenko. Yay. There you go. Ukrainian born. Yo. Very good. Alright, Anatoly Yakovenko. So now we sort of see the man behind the mask. Okay. Opposite to, say, Satoshi Nakamoto, which is good to know. No, have a little face to the name. And his email is, of course, anatoly@solana.io. Legal disclaimer. Okay, I want to read this. Nothing in this white paper is an offer to sell or the solicitation of an offer to buy any tokens. Solana is publishing this white paper solely to receive feedback and comments from the public. If and when Solana offers to sell any tokens, or a simple agreement for future tokens, it will do so through definitive offering documents, including a disclosure document and risk factors. Those definitive documents also are expected to include an updated version of this white paper, which may differ significantly from the current version. If and when Solana makes such an offering in the United States, the offering likely will be available solely to accredited investors. Nothing in this white paper should be treated or read as a guarantee or promise of how Solana's business, first typo, Solana's business or the tokens will develop, or of the utility or value of the tokens. This white paper outlines current plans, which could change at its discretion, and the success of which will depend on many factors outside Solana's control, including market-based factors and factors within the data and cryptocurrency industries, among others. Any statements about future events are based solely on Solana's analysis of the issues described in this white paper. That analysis may prove to be incorrect. Yeah. So, but you need to give up bros, man, I guess. No. No. Not giving up. I wonder, is this... Are they basically the same? Oh, they fixed a lot of the typos. Solana's business. Okay, how many pages long is this? More pages. More pages. Like, is there any significant change we should worry about? I imagine that since it's a .14 version, they just fixed typos. And that's kind of it. Right? Yeah, 32. Which is exactly the same as this guy. Okay. And then the intrinsics is... Oh shoot, they changed. High performance smart contracts. They added a little picture. Okay, this one may be better, so I'm just gonna download it. Perfect. Alright. So let's begin the reading. Let's start. Oh shoot. Oh no. Oh no, 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 no. I don't want this. Okay. This. There you go. Right? Yeah, that's perfect. Okay. Abstract. And I think actually I need to zoom out a little bit more, right? Because the camera covers a portion of this. Oh shoot. Ah, I hate that. How how do I make it so that the pages are not like this, and instead they're just listed? Page scrolling and then vertical scrolling. No, I does anybody know how to do this? Like, why is it listed like that? I don't want that. Ah, current page rotate clockwise. No spreads. Yes, perfect. Okay. So we zoom in. We zoom in until the camera doesn't cover it, which is around here. There we go. Alright. Abstract. This paper proposes a new blockchain architecture based on proof of history, a proof of verifying order and passage of time between events. Proof of history is used, or POH, is used to encode trustless passage of time into a ledger, an append-only data structure. When used alongside a consensus algorithm such as proof of work or proof of stake, proof of history can reduce messaging overhead in the Byzantine fault-tolerant replicated state machine, resulting in sub-second finality times. So they're giving us the secret to the speed. This paper also proposes two algorithms that leverage the timekeeping properties of the POH ledger, a POS algorithm that can recover from partitions of any size. Oh, really? And an efficient streaming proof of replication. The combination of POREP and POH, I'm going to call it, provides a defense against forgery of the ledger with respect to time and storage. The protocol is analyzed on a 1 Gbps network, and this paper shows that throughput up to 710K transactions per second. What is possible with today's hardware? This is absolutely insane. 710K transactions per second. Is this a hypothetical? Wait, how many Solana transactions per second? Oh, okay. I was getting scared. Okay. 4,000 transactions per second, that's still a lot. That's extremely huge. Wow. So, okay, I do not know where this number came from. The limit is being put at 65,000. 100K, okay, per second in test run. Interesting. Okay, so the numbers seem to vary a lot. I'm gonna put it on the actual, on the 4K, because it's still a lot. The Solana Explorer tells us, let's see, where do I see transactions per second? So currently we're doing 5,100 per second, which is pretty crazy. Per second. Compared to Bitcoin, right? Solana does in 1 second what Bitcoin does in like an entire hour, right? Yeah, I imagine. It's just that like it feels like a huge difference. Right? Like 5,000 versus 700. And like right, their own controlled tests run was 100K. So it's a little interesting than like 700K was given. But yeah, let's see. Maybe they justify this number later. And welcome to Ferrari. Yeah. Let's see. Introduction. Blockchain is an implementation of a fault-tolerant replicated state machine. Current publicly available blockchains do not rely on time or make a weak assumption about the participant's ability to keep time. Each node in the network usually relies on their own local clock without the knowledge of any other participant's clocks in the network. The lack of a trusted source of time means that when a message timestamp also all the participants apostrophe clocks in the network. The lack of a trusted source of time means that when a message timestamp is used to accept or reject a message, there is no guarantee that every other participant in the network will make the exact same choice. This is true. The POH presented here is designed to create a ledger with verifiable passage of time, i.e. duration between events and message ordering. It is anticipated that every node in the network will be able to rely on the recorded passage of time in the ledger without trust. Outline. The remainder of this article is organized as follows. Overall system design is described in section 3. In-depth description of proof of history is described in section 4. In-depth description of the proposed proof-of-stake consensus algorithm is described in section 5. In-depth description of the proposed fast proof of replication is described in section 6. System architecture and performance limits are analyzed in section 7. A high-performance GPU-friendly smart contracts engine is described in section 7.5. Alright, network design. As shown in figure 1, at any given time a system node is designated as leader to generate a proof of history sequence, providing the network a global read consistency and a verifiable passage of time. The leader sequences user messages and orders them such that they can be efficiently processed by other nodes in the system, maximizing throughput. It executes the transactions on the current state that is stored in RAM and publishes the transactions and a signature of the final state to the replications nodes called verifiers. Okay. Whoa. What? The leader sequences user messages and orders them such that they can be efficiently processed by other nodes in the system, maximizing throughput. Yes, it executes the transactions on the current state that is stored in RAM. What? And publishes the transactions and a signature of the final state to the replications nodes called verifiers. So the reason why I say what is this little part over here. It executes the transactions on the current state that is stored in RAM and publishes the transactions and a signature of the final state to the replication nodes called verifiers. Okay, no, never mind. This is fine. Okay, I thought it was like it was allowed to just execute the transactions without any sort of verification. Like, it would just execute them and then the verifiers would verify later after everything has already been sort of written down forever. Which, like, yeah. Okay, I may just be stupid, a stupid reader. Verifiers execute the same transactions on the copies of the state, yes, and publish their computed signatures of the state as confirmations. The published confirmation service votes for the consensus algorithm. Interesting. So we see it here. Transaction 1, transaction 2, transaction 3. It seems like they're all going to the leader. The leader computes all of this stuff and ends up with a final state of hex, 23432. Then transaction 1, transaction 2, transaction 3, another typo in the paper. They go to the verifiers recompute everything and say, yes, that indeed is the correct final state. Good. In a non-partition state, at any given time, there is one leader in the network. Each verifier node has the same hardware capabilities as a leader and can be elected as a leader. This is done through POS-based elections. Okay. Elections for the proposed POS algorithm are covered in depth in section 5.6. In terms of CAP theorem, interesting. The CAP theorem making an appearance. Let's go. Consistency is almost always picked over availability in an event of a partition. Makes sense. In case of a large partition, this paper proposes a mechanism to recover control of the network from a partition of any size. This is covered in depth in section 5.12. Partition of any size? That's interesting. Okay. Proof of history. Let's see what this proof of history that we're talking about is. So, proof of history is a sequence of computation that can provide a way to cryptographically verify a passage of time between two events. So, it uses a cryptographically secure function written so that output cannot be predicted. Oh, whoa, whoa, whoa. Yeah. It uses a cryptographically secure function written so that the output cannot be predicted from the input and must be completely executed to generate the output. The function is run in a sequence on a single core, its previous output as the current input, periodically recording the current output and how many times it's being called. The output can then be recomputed and verified by external computers in parallel by checking each sequence segment on a separate core. Interesting. That's a okay. Very good idea. Enjoy to live. Monero when? It's gonna be the next one we read. We're reading, yesterday we read Bitcoin, today we're reading Solana, and potentially tomorrow, given that the paper is a little bit long. And after that we read Monero. That's our sort of our trilogy of cryptocurrency papers. Data can be timestamped into the sequence by appending the data, or a hash of some data, into the state of the function. The recording of the state, index, and data as it was appended into the sequences provides a timestamp that can guarantee that the data was created sometime before the next hash was generated in the sequence. This design also supports horizontal scaling, as multiple generators can synchronize amongst each other by mixing their state into each other's sequences. Horizontal scaling is discussed in depth in section 4.4. Description. The system is designed to work as follows. With the cryptographic hash function, whose output cannot be predicted without running the function. For example, SHA-256, right? Gang Kamal, hello, yo. Run the function from some random starting value. Okay, so let's pay attention to proof of history and how it works. We run the function from some random starting value, take its output, and pass it as the input into the same function again. Record the number of times the function has been called and the output at each call. The starting random value chosen could be any string, like the headline of the New York Times for the day. So this is an example. We grab some random value. We've called it once, and this was the output, hash 1. We call it twice, so we call now SHA-256 on the first hash, and we get hash 2. Calling SHA-256 on hash 2 gives you this, and so on. Okay. It is only necessary to publish a subset of the hashes and indices at an interval. For example. So these are the only hashes that are being published. Okay, so what are they being published for? What are we doing with this? As long as the hash function chosen is collision resistant, this set of hashes can only be computed in sequence by a single computed thread. Yes, right, because you don't really know what is going to happen, right? You don't really know what the next hash is going to be, so you have to use a single thread. Perfect. You cannot parallelize this, sure. This follows from the fact that there is no way to predict what the hash value at index 300 is going to be without actually running the algorithm from the starting value 300 times. Thus, we can infer from the data structure that real time has passed between index 0 and index 300. Very interesting, like making them depend on the hash of the previous one gives you passage of time. I do have a question on this though. Doesn't Bitcoin already do this? Right? Because every single block is sort of a linked list of hashes, which also implies the property that like passage of time is encoded there. So what is this proof of history used for? Right? We'll see. In the example in figure 2, which I imagine is this guy, hash, oh, never mind, figure 2 is this. Okay. Hash 62F516 was produced on count this, and hash this was produced on count that. Following the previously discussed properties of the POH algorithm, we can trust that real time passed between count 912 and count 64. Timestamp for events. Okay. This sequence of hashes can also be used to record that some piece of data was created before a particular hash index was generated. Agreed. You can just embed it in the hash, right? Using a combine function to combine the piece of data with the current hash at the current index. The data can simply be a cryptographically unique hash of arbitrary event data. The combine function can be a simple append of data or any operation that is collision resistant. The next generated hash represents a timestamp of the data, because it could have only been generated after that specific piece of data was inserted. So the way we guarantee some event occurred before a given time is by adding it as part of the sort of hashing process. So imagine we compute, instead of hash 199, maybe we want to say, oh, event this whatever happened at hash 200. It means at hash 199 we append the event data, and then when hash 200 is computed, its mere existence involves the existence of the data. So the only way to recreate it is to have hash 199 and append to it the data, which proves to you that hash 200 happened right after, or happened after this little guy, after whatever the data is. Perfect. And yeah, some external event occurs, like a photograph was taken, or any arbitrary digital media was created, digital data was created. So we have SHA-256, and then you can see here at at index 336, we append, hash 335, we append the data that we want to put in, and then we compute the hash. Hash 336 is computed from the appended binary data of hash 335 and the SHA-256 of the photograph. The index and the SHA-256 of the photograph are recorded as part of the sequence output. So anyone verifying this sequence can then recreate this change to the sequence. The verifying can still be done in parallel, and it's discussed in section 4.3. Anyone verifying this sequence can then recreate this change to the sequence. True. Okay. Perfect. So we are given a little bit of a longer example with two events. Because this initial process is still sequential, we can then tell that things entered into the sequence must have occurred sometime before the future hashed value was computed. True. In the sequence represented by table 1, this guy, photograph 2 was created before hash 600, and photograph 1 was created before hash 336. Inserting the data into the sequence of hashes results in a change to all subsequent values in the sequence. As long as the hash function used is collision resistant and the data was appended, it should be computationally impossible to pre-compute any future sequences based on prior knowledge of what data would be integrated into the sequence. Oh, and the data was appended. It should be computationally impossible to pre-compute any future sequences based on prior knowledge of what data will be integrated into it. So we're relying fully on whatever this random value is. So you have to choose it very carefully, and it has to be very random. Okay. The data that is mixed into the sequence can be the raw data itself, or just the hash of the data with accompanying metadata. In the example in figure 3, input CFD40DF8 was inserted into the proof of history sequence. The count at which it was inserted was 488, and the state at which it was inserted was EF3. All the future generated hashes are modified by this change to the sequence. This change is indicated by the color change in the figure. Every node observed in the sequence can determine the order in which all events have been inserted and estimate the real time between the insertions. Okay, so you got it here, right? SHA-256 that computes this hash. There's an input here that changes sort of the course of action of everything that happens. Gele, hello, and Penguin operator is back in back. Yo, hello, Penguin operator. Yay. Okay. Okay. Verification. Let's see. The sequence can be verified correct by a multi-core computer in significantly less time than it took to generate it. For example, core 1 and then core 2, right? Given some number of cores, like a modern GPU with 4,000 cores, the verifier can split up the sequence of hashes and their indexes into 4,000 slices, and in parallel make sure that each slice is correct, from the starting hash to the last hash in the slice. If the expected time to produce the sequence is going to be this guy, total number of hashes versus hashes per second for one core, the expected time to verify that the sequence is correct is going to be the total number of hashes and hashes per second per core times the number of cores available to verify. Yes. In the example in figure 4, each core is able to verify each slice of the sequence in parallel. Since all input strings are recorded into the output with the counter and state that they are appended to, the verifiers can replicate each slice in parallel. The red colored hashes indicate that the sequence was modified by a data insertion. Pretty good. So we can imagine over here, right, that like if you have already the list of all of the hashes, right, from 1 to 700, you'd be able to simply take a look at each step in the staircase and see, okay, does computing the hash, the SHA-256 of this hash, give me the next hash? Yes. So you can just do this for absolutely every single one of them, and then you can parallelize the process of verifying, but you cannot parallelize the process of generation. Interesting. Kele. I came from mandatory AI training. I love when HR organizes things like that. It's always HR. It's always HR. Yeah. Anyways, I'm glad you survived though. Alright. I don't know why I'm so sleepy today. Okay. Horizontal scaling. It's possible to synchronize multiple proof of history generators by mixing the sequence state from each generator to each other generator, and thus achieve horizontal scaling of the proof of history generator. Mandatory how to speak English to a computer training. Yeah, unfortunate, but okay. Kelly, do you guys have something like that in your internship? So I'm no longer in my internship. I already came back to college. But yeah, so we didn't have mandatory training, fortunately. We did have these talks of like, you know, the titles of the talks that like HR gives. It's like unlock your full AI potential, right? It's like something like that, or like learn from the best in AI. Then it's like some random talk, like, right, that some person gives telling you how to set up like Claude code or something like that, and it's like, oh, you gotta have like multiple agents running at the same time, and like, oh yeah, and I created this harness and whatever. And I'm like, yeah. I feel, right, I have a bias towards not liking AI, so of course I'm gonna find those talks useless. I don't think they are useless. I just feel like I don't want to go. Fortunately, they were like not mandatory for us, but yeah. The ads I get on Twitter, yeah. I haven't been on Twitter, so I don't know what the ads look like. I imagine it's gonna be like, I mean, I guess the people themselves are already a little bit annoying sometimes, when they're like Bro, if you don't learn this new technique, you're gonna be left behind. It's like, look at this bozo, he's leaving himself behind. So it's, I don't know, I feel that's enough for me to, so I cannot imagine the ads. But yeah, anyways, yeah. Alright, let's see. People just trying to make money, mostly scams. Yeah, I imagine. Go04, welcome back. Yo ho ho ho. But yeah. Reddit, Twitter, and work. My colleagues, everyone draining my energy. So when I come back to home, I just play video games and sleep. This is true. And that makes so much sense. Like, there's something I really don't understand. I remember when I was at my internship, my mentor, which was this incredible lady. She was very sweet. Like, I really liked my mentor. Um, you would look at her calendar, and it was like meetings all day. Like, at what point in time do you code or create something? Right? Because it's always like meetings. Oh, stand up. Right. Today we have stand up. Oh, and then we have to meet with features team, or we have to meet with this team, or the ads team, or or HR, etc., etc. Absolutely insane. Corporate software engineering. Yeah, I don't know how they do it. Anyways, it's possible to synchronize multiple proof of history generators by mixing the sequence states from each generator to each other generator, and thus achieve horizontal scaling of the proof of history generator. This scaling is done without sharding. The output of both generators is necessary to reconstruct the full order of events in the system. Interesting. What? POH generator A and then POH. That's the neat part. You don't. I am senior now, and half of my day is meetings, and they are filled with AI Delulu managers. Yeah. Dude, I really feel for you. I'm so sorry, Gully, that you have to go through this. It also makes me a little bit concerned that they're using AI for airplanes. I mean, yeah, but yeah, that's all. Anyways, given generators A and B, A receives a data packet from B, which is the hash 1B. Okay. Which contains the last state from generator B and the last state generator B observed from generator A. Okay. The next state hash in generator A then depends on the state from generator B. So we can derive that hash 1B happened sometime before hash 3A. This is basically Lampport's logical clocks, just expressed in terms of hashing, right? Because as they pointed out before, you still need the full output of both generators, like all the generators, to know what happened. Yes, this property can be transitive, so if 3 generators are synchronized through a single common generator, then we can trace the dependency between A and C, even though they were not synchronized directly. By periodically synchronizing the generators, each generator can then handle a portion of external traffic. Thus, the overall system can handle a larger amount of events to track at the cost of true time accuracy due to network latencies between the generators. A global order can still be achieved by picking some deterministic function to order any events that are within the synchronization window, such as by the value of the hash itself. In figure 5, the 2 generators insert each other's output state and record the operation. Each other's output state, yes. Okay, but figure 5 is like down below, yeah. What the hell? The 2 generators insert each other's output state and record the operation. The color change indicates that data from the peer have modified the sequence. The generated hashes that are mixed into each stream are highlighted in bold. The synchronization is transitive. A, transitive with B, transitive C. there is a provable order of events between A and C through B. Scaling in this way comes at the cost of availability. 10 times 1 gigabits per second connections with availability of 0.9999 would have 0.999 to the 10, which would be 0.99 availability. Makes sense? Okay, let's see. Because you need to have all of the generators available, right? So if you have 10 of them, then you only have 0.99 availability, assuming each has 3 nines of availability. Right, new section, let me read the chat. They are not using, oh, so why are they giving you AI training then? It's banned. Oh, that's great. But they want to bring it in. So they brag the managers until they accept. Oh no! Wait, who wants to bring it in? That's a better question. Wait, why are they pushing to bring it in? Is it your co-workers? Is it like, who is it? Yeah. Anyways, consistency. Yay. Users are expected to be able to enforce consistency of the generated sequence and make it resistant to attacks by inserting the last observed output of the sequence they consider valid into their input. Oh, okay. So we're basically doing what Bitcoin does, just without the mining, which is interesting. What are the, where do incentives come into play? Users are expected to be able to enforce consistency of the generated sequence and make it resistant to attacks by inserting the last observed output of the sequence they consider valid into their input. Okay. Okay. So this generator generates this hash at this count. This generator generates this hash at this count. This hash is then sent to this guy, who now changes color because they inputted this to account for the state of this other guy. And then the SHA-256 guy, right, the red one, generates his hash and sends it to the other guy. The other guy now has synchronized with him. Okay. Okay. A malicious POH generator could produce the second hidden sequence, yes, with the events in reverse order, if it has access to all the events at once, or is able to generate a faster hidden sequence. To prevent this attack, each client-generated event should contain within itself the latest hash that the client observed from what it considers to be a valid sequence. So when a client creates the event 1 data, they should append the last hash they have observed. Okay. Wait, what? Okay, yes. So let's see, event 1 will be equal to append event 1 data, and then the hash they saw. Okay. When the sequence is published, event 3 would be referring hash 38, and if it's not in the sequence prior to this event, the consumers of the sequence know that it's an invalid sequence. The partial reordering attack would then be limited to the number of hashes produced while the client has observed an event and when the event was entered. Clients should then be able to write software that does not assume the order is correct for the short period of hashes between the last observed and inserted hash. Let's see, many people, including managers, want to find a way to integrate AI without compromising data. There are AI tools like Gemini, but just bare bones chatbots. So things like Claude Code are not allowed. I see. Interesting. Yeah. To prevent the malicious POH generator from rewriting the client event hashes, the clients can submit a signature of the event data and the last observed hash instead of just the data. Okay. Okay. So how does this work? So I agree, we sign the data, then any POH generator can just verify with the client's public key. Okay. So my question is, the client appends the hash of the last block they saw and considered to be valid. But it's very possible that there's just other sort of chains taking place at the same time. Other sort of proofs of history. Alright? And so what happens if the client picks a hash that the server it is sending the information to does not agree with? Right? I imagine, unless you have to use the hashes that the server you're sending things to is using. Verification of this data requires a signature verification and a lookup of the hash in the sequence of hashes prior to this one. Yeah. In figure 6, the user's blind input is dependent on hash deadbeef, existing in the generated sequence sometime before it's inserted. The blue, okay, the blue top left arrow indicates that the client is referencing a previously produced hash. The client's message is only valid in the sequence that contains the hash x deadbeef. The red color in the sequence indicates that the sequence has been modified by the client's data. Okay, so client user event hash dbad is generated with the hash deadbeef. Okay, it links deadbeef to the next generated block, bad code, which prevents a malicious loom from reordering the events in a hidden side sequence. Interesting. So we attach it, okay, we just use the last hash we saw, we append it to the data, and that is now part of the next input. Okay. Okay. Let me read the chat. I have a fun topic for you to read or work on next. Ooh, I think you may like it. It's deterministic lockstep networking. i.e., how would you make an online game without an authorizing server? Peer-to-peer validation in multiplayer games. Yo, this seems pretty good. I agree this sounds interesting. It still plays into the distributed sort of, trustless model that we've been looking at. Theodore, yo, what's up? I'm good. How about you? Yeah. Being a little sleepy for some reason. I don't know why. Woo. Okay. 4.6 has overhead. So 4,000 hashes per second would generate an additional 160 kilobytes of data and would require access to a GPU with 4,000 cores and roughly 0.25, 0.75 milliseconds of time to verify. Pretty good. Wow. Damn. Okay. What's your hobby outside programming? So usually, it depends. Since given that I'm in college, I usually just spend all of my time studying, and when I don't study, I just like to code, like fun things. So I honestly consider coding to be something fun that I just do. Outside of programming, I'm starting to learn how to play the electric guitar, and it's something I want to do. I haven't practiced much lately, but I should keep on practicing the electric guitar. Um, yeah, mainly that. I also used to play piano. I don't have a piano, of course. So, that is kind of lost and gone. And other than that, it's just sharing time with friends, going out, doing something. But, yeah. What's your favorite album or artist or band? Which is, it's an interesting question. I feel like I just have 5 artists I listen to, and that's it. So mainly I listen to this girl called Aurora Axnes. Very good. I like Aurora a lot. I listen to Cage the Elephant. It's sort of the rock band I like and I listen to a lot. Bomb, which is this French singer, very similar and it's sort of around the same category as Aurora. Hosier, very popular here. Very good lyrics and everything. And the last was Milky Chance. Milky Chance are the ones that did the like stolen dance, you know. I want you, we can bring it on the floor, never dance like this before, right? I you know, that song is the one most people know, but I like other of their songs that are maybe not as well known. But yeah. So for example, oh, you're giving an example of the network in lockstep. Okay. What Warcraft 3 does is play one sends guys, I'm moving to this position, and every other player says either wait, you can't do that, or go ahead, sending these messages to each other. If approvers are higher than rejectors, they do it. Every once in a few seconds, they send the full game state to verify no one is left behind. Interesting. But one of the things that I'm sort of concerned about is like the network overhead that implies. Like, would it be just too much? Like, characters move continuously. So I'm imagining something like Minecraft or you're right, like Warcraft or something like this. Players move continuously. So like a player could just move like 0.1 centimeters if somehow, you know, 0.1 pixels, let's say, right, which is a better 0.1 pixels, right? Then they would need to send an update for those 0.1. And then after that, they need to keep sending updates and updates and updates and updates, right? Everyone has game engines, so physics, etc. are calculated locally. It's user input that is sent continuously. Ah, okay, I see. Then how do you trigger mouse events? Because mouse events are still user input, they're still continuous, so they must be sent basically all the time. In Minecraft, you can see like people's heads moving, so it means that it is sending these types of things, but wouldn't that generate a lot of overhead? Instead of sending W press every... Yes, that's what I imagined for the W, because if you have just W pressed, then you just say, oh, lock W, and then after they release, it's like release W, right? That makes sense. With mouse, it doesn't make so much sense to me, because you can just move your mouse in the most random directions ever, and then it means that you would be sending thousands of packets, each of which like milliseconds apart from each other, just to track the movement of the head of a player. So I'd be interested in knowing how that goes, or if they, like, does it actually just send it? For cursor, it's similar. Other users don't need to be picture perfect aim. So then what happens with games that actually do? Say like Fortnite, CSGO, etc., where like the specific place a player is looking at when they shot a bullet is extremely important because it determines the trajectory it's going to follow, and then could kill or not kill somebody in the process. So, oh, those are not peer-to-peer, there's an authorized server involved. Yeah, so does it mean that such a game is not possible to support peer-to-peer? Or like, are there any techniques related to that? I guess that's the interesting part of it. I may look into it. We'll see when we decide the projects. And in fact, if I remember correctly, I have a list of projects that we wanted to do. So let me, I think it's in tutorials, perhaps, unless, no. cd./reset ls. Okay, I want to say it's learning resources. Cryptography, no. Okay, these are the ones that Jasper gave us. I think I'm just gonna create, touch. Okay, project ideas. Okay. Yes, and then let's micro that. Okay, so we have, I remember it was the gits. Gits. I'm just gonna call it that. We also have the idea of, let's see, what was the name? Network overlocking? Deterministic lockstep networking. I do want to get into networking. I feel it's like one of the things I'm interested in because I haven't explored that much. So maybe doing like networking from scratch of some sort. As you saw in my folder, I have this one folder called networking from scratch because I was exploring things that would allow you to, because I wanted to like build networking from the networking stack from scratch. So I have it here. That could be an interesting project too, we'll see. League of Legends uses, I think, eNet, and Valve uses Valve Networking Sockets Library. Interesting. Okay. You can send that much information over UDP? Really? Damn. C-Scale. Hello, my friend. Yeah, we're still reading the Solana white paper. So yeah, both are open source. Oh, pretty good. Take a look at that. Alright, let's see. So we now take a look at the attacks section. Right. So I think we can stop here because it's like halfway through the paper. And we'll take a look. Let's see. Attacks. Reversal. So generating a reverse order will require an attacker to start the malicious sequence after the second event. This delay should allow any non-malicious peer-to-peer nodes to communicate about the original order. Okay, generating a reverse order would require an attacker to start the malicious sequence after the second event. What does that mean? A reverse order. My thing is like, didn't we just solve the reverse order attack? Because the client sends the hash, the last hash that they saw. Right? So I'm not really understanding why this is a concern in the first place. Okay. 47.2 speed. Having multiple generators may make development more resistant to attacks. One generator could be high bandwidth and receive many events to mix into its sequence. Another generator could be high speed, low bandwidth that periodically mixes with the high bandwidth generator. The high speed sequence would create a secondary sequence of data that an attacker would have to reverse. Okay. Long-range attacks. Long-range attacks involve acquiring old, discarded private keys, okay, and generating a falsified ledger. Proof of history provides some protection against long-range attacks. A malicious user that gains access to old private keys would have to recreate a historical record that takes as much time as the original one they are trying to forge. This would require access to a faster processor that the network is currently using, otherwise the attacker would never catch up in history length. Okay, a malicious user that gains access to old private keys would have to recreate a historical record of, wait, long-range attacks. And generating a falsified ledger. Okay, proof of history provides some protection. A malicious user that gains access to old private keys would have to recreate a historical record that takes as much time as the original one they are trying to forge. This would require access to a faster processor that the network is currently using, otherwise the attacker would never catch up in history lane. Additionally, a single source of time allows for construction of a simpler proof of replication. Since the network is designed so that all participants in the network will rely on a single historical record of events, PoRep and PoOH together should provide a defense of both space and time against the forged ledger. Okay, let's see. The thing is, if you send cursor 100 times, only important one is the latest one. So even if UDP drops a few packets, it doesn't matter. True. I'm also making a game over on the side, sometimes with Enid, so I'm kind of familiar. Although my game is server authorized. I see. Wait, pretty good. Alright, I think we reached 10:30 a.m. Which means, you know, it's time to take a break, a small break. Yeah. Let me check. Yes. Break from 10:30 to 11 a.m. So we'll be back at around 11 a.m. So it's gonna be like around 30 minutes of wait. So yeah, that's mainly it. So yeah, let's do that. I'll see you guys in like 30 minutes, probably. And yeah, I'm just gonna take a break. Yeah. Before we transition to perhaps Rust, I would say is the next thing we do. Okay, I'm gonna put on the starting soon screen with taking a break, and we'll see you guys. All right, let's take a break. Stretch, stand up, drink a cup of coffee, a cup of water, drink something, and I'll see you. Hello. Hello, everyone. Oh, welcome back once again. Glad you guys are here again. I had a nice break. It was, it was laid down for a few seconds because I'm weirdly sleepy. I don't know why, but yeah. All right. So yeah, time to develop code. Let's go. Okay. Let's see. So, what can we do? So I'm gonna open here the coding scene so you guys can see what I'm seeing. And let's take a look at maybe, okay, so this is workspace one. I don't want the workspace one. Let me close my email, all of this. So in workspace one, we can put the, actually that's the Visual Studio Code, right? Yeah, okay, so last time we sort of finished this crucial section of Rust links up until lifetimes. And now these guys are left. Now, I'm a little lazy. I I find it a little bit boring when it's just like exercises and it doesn't really need you to do anymore. Like, we did all of this just to sort of get familiar with the syntax of Rust and the concepts of Rust. And so now we can proceed to maybe do something better with Rust. So I'm going to propose starting our own sort of cryptography module in Rust. Okay? Applying sort of all the concepts we learned in Joy of Cryptography. I think that's, I don't know what you guys think about that. I feel it's like the best way to do it because we're gonna encounter a lot of points where we don't know how to do something and then we're gonna have to explore. But at least it's related to our project, so we can at least start sort of working a little bit on the project while we learn Rust and while we finish sort of reading all of the previous knowledge that we need to acquire. So yeah, I don't know. What do you guys think? So let me actually maybe create something here new. What should we call it? That's a great question. What is a cryptography module called? What is our blockchain gonna be called? I think, okay, for now I'm just gonna call it cryptography. Okay, cryptography, that's it. Oh, sorry, I forgot to, shoot, okay. Cryptography, and then slash, perfect, so that's my folder. And I think this is it, right? Like, I don't think I need anything else. So I'm just gonna open this one. Perfect, cryptography. So now, inside of cryptography, yeah, let's begin. So how to start a Rust project. I remember it was something like Rust in it. There was something like that, or like cargo in it. Yeah, it's a cargo new. Build your project, run it with this. Cargo new my project, right? But like, does that generate a folder? Or does it do it in the current folder? I guess there's only one way to know. Trust folder and continue, yes. What happens if I... Brother, what happens if I... Come on, okay. Cargo new, say, test. What? Oh, okay. There was an app playing in the background. Creating binary, invalid package name test. It confirmed it conflicts with Rust's built-in test library. Oh my god, okay. Cargo new, test, 1. Oh, so it generates the entire folder. Okay, okay, okay. I see. Um, how to delete a project with cargo. Can I just delete the folder? Okay, yes, yes, okay. Because this sort of made me think that there was some sort of registry for all your projects, and I was like, damn. Uh, so like there must have a command that allows me to eliminate it from the registry, but it seems like not. So let's just delete this. Perfect. So I think what we're going to do is actually, I think we can just go to projects and then RM cryptography. Cryptography and then RM there. Perfect. And then we can say cargo new cryptography. Perfect. Alright. So we cd into cryptography. And then we code here. Great. Let me just close this one and then make this full screen. Yes, okay. Perfect. So we have all of these guys, and then we have main.rust. Oh my god, this is gonna be epic. Okay. So what are we gonna do? Great question. Great question. I don't know. So one of the things we are definitely going to pay attention to, right, is the fact that so we need to somehow develop. How would you do this in the first place? Like, how does a crypto library work? Right? What are its components? Because one of the things I'm thinking of is this sort of. Okay, so one of the things we do need to implement. So what am I talking about? We're going to create our own crypto library. It's going to be very simple. Well, not very simple, right? But like I mean that it's not going to be the last Coca-Cola in the desert with all the features and everything. It is going to include the basic things. Okay? Now, my question is, what is included in the basic things? And how do we do it? So for example, right, I could say Diffie-Hellman is part of the basic things. Sure. How do we sort of symbolize Diffie-Hellman, right? Because Diffie-Hellman involves sending messages to another party. But it seems like that part of sending the message is not the responsibility of the crypto library. So it seems like we just have to implement these sort of modules of sorts. Like I am not very sure. So what happens if I just create a file called crypto.rs, right? And then, okay, so what are the contents of a cryptography library? Is there some, yeah, cryptographic libraries. There you go. What is the cryptographic library? SHA-3. Okay, so it just includes all of these things, right? Encryption, decryption, hashing, digital signatures, key management, and asymmetric. Okay. Sure. Okay. This seems like a good encryption and decryption, hashing, digital signatures, etc. Okay. Let's begin with that. Let's begin with this little list: encryption and decryption. So what can we do to start with encryption decryption? Let me actually turn the lights on here so that it looks like I am a professional despite not being one. There you go. How does it look like now? See, before it was like this. Now it has a tint of yellow. Okay. You're very familiar with VS Code. Well, not too familiar, but I mean, the minimum amount of familiar that I need to work. But yeah, so let's see. So crypto.rs. Perfect. Now there's gonna be sort of questions that we're gonna have all the time. So let me move these things around. Sorry, my bad. So instead of doing this, I feel like what I want to do is, yeah, there you go. So how, no, modules in Rust. I forgot already. So let's revisit modules in Rust. Oh shoot. Okay. So module is mod and then my mod and then functions. Okay, perfect. So let's take a look at that. So imagine that our entire crypto thing is gonna be involved in a library, right? Or like a module, right? And I'm gonna call that module crypto maybe, or what should I call it? Yeah, right. Calling it crypto. I feel like calling it crypto is the wrong thing. Because I want to separate it into modules: encryption, decryption, then sort of key exchange, right? These specific the specific sort of key categories. Um, so maybe we can name this one, EncDec, like encryption, decryption. This is the module of encryption and decryption algorithms. Seems reasonable to me. Great. And so what are the things that we are going to have inside? So I imagine we can have nested modules. Can I have a nested module called RSA? Yes, it seems like it can. Right, EncDec and then RSA. Okay, seems like it supports it. Is there a way to get rid of all of the sort of white space and tabs that we need to put here? Right, because it feels a little bit annoying. It's how to create modules in Rust without tab white space. I don't know how else to describe it. Tidy style. So how do I... Yeah, I don't... Maybe nested modules in Rust. What? Okay. So this, like, what am I... Yeah, this, I hate this. Can I... Oh, file-based. Okay, this is just for syntax, right? I'm using the overview for the sake of syntax. Because, like, yeah, I just want to know if I can just not use humongous, a huge, cascade of modules. Let's see, the parent and the root. Create a child inside the parent. To look inside the network folder for protocols.rs file. Interesting, writing code in the child file. I see, so I prefer this model of separating modules as files. I think that's what Odin does and what Golang does, and I feel it's like way better. So I'm going to include the crypto module, and then inside here I want to say EncDec, right? And EncDec will include, we'll see what it includes. So let's move crypto.rs here. And from what I understand, let's see. So main.rs needs to declare that they want a module called right? Wait, I don't understand. Main.rs, right? Then we need to include in here the module crypto. Crypto, yes, okay, it recognizes it. So crypto, if this was inside the crypto folder, would it have recognized it? No, okay, interesting. Mod crypto. Sorry, I put in mode. File not found. Okay, if I specify the file. No, okay. So the file needs to be at the top of the folder, that's fine. And so now it recognizes this folder as belonging to this file, or this file being able to reference it. Okay. And then here, I see. And so now the module that we need to load is encdeck. Right. Because here we're going to have, sort of inside the crypto folder, we're going to have encdeck.rs. And then that error should be solved. Yes. Okay, that makes sense. And so here in encdeck, we can start sort of creating our modules. Okay, so I would say module RSA. So we need a module for RSA. Right? Oh, it seems like they don't allow that. So, okay, right? Encryption, decryption. Maybe there's RSA, right? Or let's say. So, will we separate it into symmetric and asymmetric? Do we separate it into asymmetric? Like, Give me a second. I'll be back. Hello. Hello. So, we're back. Damn. Okay. All right. I don't know why this light started to fall down. There you go. All right, perfect. So, question is, how do we organize this, right? We have the crypto. So how would we want our calls to be, right? Something like crypto, and then data, something like encode, decode, and then RSA. I feel this is sort of the thing that I would like. And for this purpose, I think we can just open joyofcryptography.com again. Can take a look at RSA and remember exactly what the sort of procedure was, right? So here we have all of these guys. Sure. So we need the key generator for RSA, right? Key generation, I imagine. So does it fall within? Yeah, it falls within the responsibilities of the RSA module. So RSA keygen, and then here we have encryption and decryption. Yes. So the keygen, encryption, and decryption, and in fact, this is part of the syntax of a public key cryptography module, if I remember correctly. So if we take a look at this, it's defined as this. So we need keygen, enc, and dec, right? So let's start with that. Inside the enc dec module, sorry. What we're gonna want to do is say something like, okay, enc dec module. I want to separate them into files just because I like them being organized. So rsa.rs. Okay, so here we're gonna have the RSA module. Great. So now we can actually start. So how would this work? The RSA module would define, so modules in Rust with files. So separating modules into different files. Here, mod. Okay. Pub function list alternative file paths. Okay, wait. Does it tell me? No. Okay. So, for example, let's start from the code that had multiple of these. Okay. As shown, the compiler knows to look in this file because it came across the module declaration, the create root with name front of house. Okay. So we go there and then okay. Part of the project, yeah, other files in the project should refer to a load of files. Yes. Module to its own file. The process is a bit different because hosting is a child module of this, not of the root module. Hosting in a new directory that will be named for its ancestors in the module tree, in this case /front. Yes. To start moving hosting, we change /front of house contain only the declaration of the hosting module. Yes, pub mode hosting. Then we create this guy in a hosting RS file. And so we can just declare functions and they would be considered as part of the module. Okay, that is absolutely awesome. So we can create a function, public function keygen, right? And keygen is going to do exactly what it needs to do. It accepts no arguments and it generates the key, right? So it generates RSA keys. Then we're also going to have encryption, right? So public function encryption. And then we're going to have the public function for decryption. Perfect. Okay, that's very good. Do you have a module manager in Rust? No. I don't have anything installed other than the natural module manager. Like Rust does it all by itself. So let's take a look. So the public function keygen over here, right? We want to focus on it first. Let me close these guys. Actually, let me delete them because that warning makes me angry. So keygen, how do we generate a key for RSA? So remember, we need a public and a private key. Okay? The public and private key are going to complement each other modulo the totient function of our group. So there's going to be some information that this keygen procedure is going to require. And that's going to be n. That's sort of like the two prompts that we're going to have. Andrew, hello. We are coding our own crypto library in Rust now. You know, Rust links gets a little bit tiring, to be honest. And so I'm trying to have like a little bit of a more application focused learning in a sense. So yeah, that's this keygen guy. Okay, and then let's go to Jove cryptography. So when we talk about keygen, right, it generates the public key and the private key. We remember that for RSA, we need to have them be complements of each other, be sort of the inverses, so the exponents, modulo the Taussian function, right? So there are things we would have to give to this sort of keygen procedure, no? Because we need to decide what the n is, what p and q are. We need to decide like all of this stuff. So I'm a little confused by the fact that it says it takes no arguments. So if we go back to the RSA chapter, right, and then we take a look, are you going to make it just work algorithmically, or are you going to make it in a way where it doesn't leak through timing attacks? So I think for now, we're going to do it just algorithmically because I'm not at all familiar with Rust. So the algorithmic approach is a way to get me like working with Rust and be like, okay, Rust works and it makes sense, right? And like how the syntax works, you know, applying all the things we've learned so far. So yeah, that's the main thing. I think it's going to be algorithmic. If later maybe we can decide to prevent the timing attacks. So yeah. Try to take a look at the keygen. So keygen, right? Keygen, oh, keygen is the one that returns all of these. N, E, and D. Okay, perfect. Perfect, perfect. So I say keygen returns all of them. Very interesting. So N, E, and D are the things that we're going to return. And so one interesting thing to consider would be, well, right, this function would have to return a tuple. Ooh, we're using Rust. Let's go. So it would return, oh, I don't know why I closed that. Oh, yeah, no. So we have a table here on the amount, you know, the following table shows for a given target value lambda, how much the modulus must be so that these factoring algorithms require 2 to the lambda effort. The modulus being n, the size of n the size of n in general. So usually n is 3072 bits. I don't think you guys can see this because it's very small, but it says 2 to the 3072. And so what that implies is that we need to select our primes through sort of our, you know, what's the name? We need to select primes that are like what, 1536 bits long. So that would be the first thing. So it's gonna be like P, and then it's like, you know, draw a random prime from like, you know, 1536 beats. A random prime of 1536 bits, and then do the same for Q, right? We would need to draw a random prime of 1536 bits. Perfect. So we have P and we have Q. Now, what do we need to do after that? Right. By the way, did you figure out how to get random numbers in Rust yet? No. That's the whole reason why we're doing this, right? We're like discovering the things that we need to discover as we go. So that's the reason why we're doing it. And that's why I included it as a comment. I'm just sort of creating the, what's the name? The sort of schematic of the thing. So this is going to be let P and then let Q. P and Q are constants? Yes, they are constants. Then we need to also generate E and D. So how do we generate E? Let's try and recall it from our memory. Try and remember. So E is the public key, D is the private key. I think we can just The totient function is the product of two numbers, and e needs to have an inverse. How? Okay, my intuition just says like grab a random e, but that's not true, because we're not guaranteed that that guy has an inverse, right? We also wouldn't be able to compute it. So, okay, actually, no. We can grab a random e, right? It's like grab a random e, right? Then that random e, we know that x to the power of, yeah. What was it? Let's reread. Let's reread because I forget. I forget exactly how we extract e. Let's see. Yeah, okay, GCD, right? Algebraic properties, good. So we have the totient function, yes, of the proof. Perfect. Euler's theorem is if this guy belongs here, then e da 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 da. So it would be like e to the totient function. Yeah, there you go. So random e, and then d would be equal to e to the power of totient function or something like this, minus 1. Totient minus, like totient minus 1. Something like that. Let's see. Yeah, in other words, this, the number e is da 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 more than a multiple of phi of n. Yes, no, I agree, Andrew. For now, I'm just drawing the schematic, but yeah. Euler's theorem motivates the following RSA functions, which would be let n be the product of two distinct frames, and let e and d satisfy them be an equivalent modulo the totient to 1. Right? Yes, that makes sense. Perfect. We choose exponents. They must be multiplicative inverses, mod phi n. So we must ensure they are chosen relatively prime to phi of n. And this was my concern, right? But like, if you choose a random e, okay, so he just does, okay, so just choose random e until you find one. I see. Okay. Yeah, okay, I see. So we just grab a random guy, and then we compute its inverse. Wait, this is not necessarily correct, right? Because grabbing a random e from z multiplicative and then totient n is not... Oh wait, never mind. No, everybody has an index in the multiplicative group. Okay, why are we grabbing it from the multiplicative? What? Oh, because everybody in the multiplicative group has... No. What? Okay, wait. I'm getting very confused. What am I doing? What am I doing? So E mod phi of n, right, more the multiple of this guy. Yes, so we effectively, the way we encrypt is this, the way we decrypt is power of d. When we do the key generation, we choose an arbitrary, yes, we define n to be that, perfect, that makes sense. The problem comes when you draw E, right? Z star is defined as all of the elements that have an inverse. Okay, all of the elements that have an inverse in totient n. We grab a random element with an inverse. And my question is, like, this inverse refers not to the inverse in this group, but to the inverse in the addition group? Like, what are we... doing here? Let me think. Actually, no, it has to be the multiplicative inverse. So never mind. Because we're going to multiply them together. Okay. So, what I was saying is like, if you pick this up from C star and then, you know, totient, so it's like phi of n, right? If you pick this randomly from here, then this group is a different group from this guy, and they just behave differently. So is D interpreted as an inverse on this group or an inverse on this group? From what I understand, is an inverse in this group, because we're gonna end up multiplying them together in order to decrypt, right? And so they would need to be multiplicative inverses, and the sort of implicit operation in Z star is multiplication. So perfect. We draw a random E that does that, and then give me a second, guys. I think I'm gonna remove this shirt because it's cooking me alive. It's cooking me alive. Like the heat this thing generates is insane. What the hell? Okay. There you go. I have like a little t-shirt under, so that's what I'm gonna use now. I know it's not my usual uniform. I always use shirts, but this thing is frying me on the inside. Alright, so we have random E, perfect. We have D, and then we return all of them. Okay. Sure. So now, here it would be like let M be equal to P times Q. We're not going to use them in the future, and so these guys are completely fine. Okay, perfect. So what are some of the things that we're going to need? We're going to need, let's make a list here of all the things we don't even know. So we don't know, 1, how to draw a random number in Rust. That we do not know how to do, right? The other one, how the hell are we going to represent an element of Z star and then phi of n? So of course we're going to use a number for it. We just say the first element, the second element, the third element. It's just that like how are we going to discover the elements of this guy? I guess it's a better, right? Right? Great question. And what else? 3, how to handle humongous numbers, huge numbers. Okay. So for the first one, we'll take a look at it. We'll see how to handle big numbers in Rust. Num big int and then big numbers in Rust, says here. How can I deal with numbers in Rust such as 2 pow 64 or 2 pow 128 and bigger ones? U64 is already small for example, 2 pow 8, 2 pow 64. Yes, this is true. Also, the max value of U64 is 8 bytes, which is this guy. Correct. 2 hex digits. What you showed there is 4 bytes. Yes, hence the name. You also have this guy. Yes, for bigger numbers, please take a look at this crate. So the big int crate. Oh, interesting. There's num big int and then there's big int. Ungroup tabs. Okay, so they are different. Which one should I use? Oh, marked as unmaintained. See this guy. Okay. Use uint instead. What the hell is uint? What? Huh? Okay. Big int. Can we look up for the uint crate? Yes, okay. Provides facilities to construct big unsigned integer types, which is no allocations. Yo! If you want to use a predefined type, take a look at here. Okay. The focus on the provided big unsigned integer types is performance and cross-platform availability. Support a very similar API as the built-in primitive integer types. Okay, construct your own big unsigned integer type as follows. U1024 with 1024 bits consisting of 16 times 64-bit words. Okay. So is it always 64-bit words? The basis of things? I have no idea. What the hell? Okay, what am I supposed to use? Num big int? No, this seems even worse. Big number crate. Okay. Hi guys, there are multiple crate options to handle large integers. I'm wondering what is most widely used and why. I know there is a num begin crate, but from what I've heard, it is not that fast. I've seen benchmarks that malachite is pretty fast, but it seems to still be in the early stage of development, and there's not much documentation I could find. P.S. I don't want to use rug since it is not pure Rust. I like -u the most. It's pretty Rust. It's pure Rust. Very modular and non-GPL. -u seems pretty good. I wonder how its performance compares to other big num crates. I haven't seen benchmarks, thanks anyway. I never run it before there's a benchmark subproject in the -u repo. Okay. I big -u. I don't really care that much about the benchmarks, to be completely honest. So, Ruggy suggested second one goes to -u. So, okay. Why do people not like Rug? They say it's not pure Rust, but like, what does that even mean? Rug and then -u. Okay. Put numbers with arbitrary precision and correct rounding. I feel like I would like it to be more like a similar to what we saw with the uint one, because the uint one had a very, very good. I feel like I liked the uint guy. Right? The problem is like, it is not clear to me whether I always need to think of this as 64-bit words. Other than that, it seems pretty cool, right? I don't know, what do you guys suggest? Maybe somebody has an idea? I want to see the syntax of -u. Because better create searching website, lib.rs. Oh, wait, so then what is this? Why are there like multiple websites? Okay. So one of the things that I see, it's like, I don't want it to be like arbitrary precision. Because if I'm able to specify like the exact amount of bits I need and, you know, not have to run all of the overhead required to support arbitrary, you know, arbitrary length integers, then it'd be better, right? I just want something minimal, and it seems like uint provides it. It just tells you how to declare your own thing. And I like that. So name, keywords, description, so big numbers. Byte order, numbigint, big decimal -u. Okay, how about we use uint? It seems the one that's more akin to what we want. Everything, so I think I'm just gonna do that. No. documentation is here. Okay. So construct uint, unroll, whatever that means, from hex error. Oh, what the hell? And then enums. This is very incomplete. What the hell? How am I supposed to know what to do? Okay, how to use uint in Rust. Uint create in Rust. No, how to use uint create in Rust. So, thank you, but there's also this. Okay, yes, let me take a look at that. There's ruint, but what are their differences is my question. Wait, why is it not letting me select it? Thank you, GraphiQQ. Let's take a look at this. So, I had opened something like this before, but uint is macro-based, is generic-based, more modern kinda. Okay, I see. So that's good, right? Like, I just wanted something that would allow me to specify the specific amount of bits I want this number to store. Right. And so doing it as uint and the number of bits, I think is exactly what I needed. But let me take a look at how. So are there any more references of like how I can use this maybe? What is this uint macro? So it seems to be more like a uint class type of thing. So let me see. Where is it? Uint. Where is it? Ah, here. Uint. The ring of numbers modulo 2 to the bits. Oh, this is perfect. All traits and methods from the std integer types. Perfect. Okay. Seems like both uint and ruint depend on num big int. Really? Well, that's interesting. Okay. So guys, I'm the one that doesn't know about Rust, so you may have to help me with this. Which one is the better one to use? I just don't want to include a bunch of overhead in the project. I just want something simple, right? Like, because NumBigInt allows for arbitrary precision. I mean, we could use it. I don't need the arbitrary precision. Yeah. Okay. Ruint is sounds like what I want. Sure. Okay. Let's try ruint. Overflow negatives. Okay, let's try it out. So, if I remember correctly, it was something like cargo install and then the name, ruint. There is nothing to install in it because it has no binaries. Programs. Cannot be used with libraries. Oh, sorry. It's cargo add ruint. The Rust way to grade programmer. Hopefully, cargo add ruint. Let's see. What the hell? Why? Why are there so many dependencies, bro? What? Bro, I just wanted dependencies for my big integers. What? Why did you download half of the crates in the world? Oh no. And now your compile times will take a decade, bro. No. Dude, no. Android system properties? Why would... Okay, this is pissing me off. Like, what the hell? Just to, you know, just to spite the Rust people. Big integers library C++. C++. Brother. GMP lib. Okay. Oh, it has it's built in and it's pretty simple to implement actually. Wait, to implement like arbitrary precision integers? Dude, C++ has its own. It's standard big int. What? Because CMake sucks. Wait, no, that's great. Like, the fact that CMake sucks, it's like actually kind of great. Because, like, it stops you from being too stupid and including like 10 gajillion dependencies. But, yeah. I wish Rust had a lot of what you need part of the STD. Yeah, same. This is a little depressing. Because, okay, now it's gonna be very bad because, ooh, okay, how do we do this? Because we, not only do we need something that supports integers of a given, like, amount of bits, we also need something that is able to make random choices on integers with a given huge amount of bits. So what do we do? You could argue like, oh, just go like 64 bits and 64 bits and just generate a random 64 bit, then the next block random 64, the next block random 64. But like, is that really the way? Like, I don't know. So you also need a random big number generator. Also, how do I delete packages in Rust? Cargo uninstall, cargo remove. Okay. So I have a question. If I do cargo remove, ruint, right, which would be this guy, will Rust realize that not only do I need to get rid of this package, but I also need to get rid of all the other ones? Because it just installed 20 gajillion in my PC. I just want to test. If I do this, will it uninstall the 20 gajillion? Let's see. Oh, brother. It did not do that. Oh, no. Cargo tumble. Okay, I mean, I guess... It's okay. Well, alright. URCHIOX, yes, we need 1536 bits, random number drawer. So we need to draw. What happens if I just say, like, your log file shows all your transitive dependencies. You can see if it still depends on that. I see. So, wait. What happens if I just do random, like, big number, random number generator, Rust. Rand. So num big int. What? Hello. Okay, wait, how do I do? Wait, what? I thought cargo remove gets rid of some dependencies. No, it doesn't. That's why I wanted to try it out. Because I'm like, surely it doesn't, and then precisely. There you go. It didn't. Random numbers with it. Ah. Okay, so how do we solve this? How do we generate like random numbers with big integers? Does any of you guys know? The only way to maintain good compile times in Rust as your project grows is to implement everything yourself in a simple manner. Okay, I need to attend something, man. I'll probably be back later. Great. I'll see you, YouTubers. Thank you for joining the stream. Oh. We're gonna. Okay, what if we. Noon begins. It didn't show you depending on all other dependencies. You technically want. Yeah. It's okay, it's okay. Because, like, now they're installed on my system, right? So they're taking disk space without, like, doing anything. So, anyways, it doesn't matter. They're very light on engine, so. Oh, wait, it's very easy to generate large random numbers. Wait. So you can treat them the same way we would treat other numbers. Large Fibonacci numbers. Big UNT, okay. Large random numbers. So rand, noon begin, okay. But in most cases, you probably want a non-deterministic RNG. Okay, yes. Be RNG.random begin. 1,000. What? Wait, so rand just has this thing? Yeah, random generation. New begin supports the generation of random big integers when either of the rand09 are enabled. The big RNG and big RNG traits provide extension methods for any rand core RNG of their respective version. Fulfill further functionality for random distributions in randistor. If you run cargo build, it will drop the transitive ones from your log file, I think. Okay. Know that you must use the same version of rand as the feature you enable in non-begin. What? What? Oh my god, no. Dude, okay. Ah! Wait, how do I even do this? Like, test it for Rust 1.6 and greater. Dun, 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 dun. Okay, yeah, what am I supposed to do? Random big in range. So it's like RNG and then. Okay, so it seems like we're gonna have to end up using big int, right? Unless our. Okay. Generate random argument numbers Rust. No. Big numbers. Dude, okay. Because my only intuition is since twint, I wrote twint. Oh, yeah, you're right. RUint, yeah. Okay, so what I can imagine, it's like RUint depends on big int, and so I can just feed it into rand, and rand won't notice. right? Right. So it seems like I'm going to have to use rand. Let's take a look at rand. So do I do cargo add rand? Or like, oh, I think Andrew suggested I put it here. How to add a dependency to cargo.toml, because I don't know the syntax of cargo.toml. Okay, dependencies, okay. And then I imagine it just use two separate dependencies for random and begins, but find a way to string them together. Yes, I know, but like, if they are already stringed together, then that's great. Like, because then if I have to find a way to translate between the two, then it's like honestly kind of lost time. Like, might as well have implemented them from the start. Rand, right? Rand, and then what is the last version of rand? Rand, give me your version, please. 0.10.2. Yay. And then ruint, which would be, let's see, can I find a crate called argument? Yes, 1.20.0. 1.20.0. Yay. Okay. We got that. And so what we can do maybe is we could say, okay, how you can do start and we'll pull the latest version in log file unless you want to pin. I'd like to pin it sort of like the same way it would be in like C++, where you just download the thing and it just stays like this forever and there are no breaking changes. Yeah, I just want to have it like that. Okay, so how do we generate a random guy? Can I look for the word random? Ooh, rand implements. Oh, look. I did a random alongside some. Wait. So we are able to work with rand, right? Oh, it took us to the same. Okay, wait. Let me close so many tabs. I hate having so many tabs open. What the hell? Okay. Bye. Okay. Then you can commit the log file and add locked to cargo build. Anyway, both ways are okay. I see. Try to never use this kind of auto-updating version strings. This easily causes supply chain attacks. Yeah. That's what I imagined. Like, that's why I like the C++ way of just having it there. Yeah. RPC 2.0. Welcome back. But yeah, okay, so what do we do? How do I generate the numbers? Yes, so let's see. Can we somehow get this working? Please! Okay. Extern crate. And then I'm gonna say ruint, right? And then another extern crate called rand. Perfect. And so it says here that I should create an RNG. What does that? Okay. Well then, where's the guy that we were looking at? Brother. Okay, RNG. This guy. So we saw it in the features. It listed this thing, rand, and rando9. Implement sampling from the standard uniform distribution, i.e. RNG to random, alongside some utility random methods on uint itself. But it says there is support for number crates. These are enabled by setting the identically named feature flag. How do I set the feature flag? What does that even mean? Okay, if I do something like, let's see, can I call rando9? in cargo toml in the dependency. Okay. So I have rand. So are you in? Okay, wait. How to set a feature flag in Rust? Features. Create version. Okay. So do I do ruint, and then I do this guy, where I say version equals this 1.20.0, and then I set the corresponding thing. Feature flags allow a project to conditionally depend on other projects. If you're not using any dependencies, you won't compile extra code. Okay. Features is equal to an array, and then I imagine that it's called rand09. New line is not allowed. What? In an inline table. What? That's so dumb. What the hell? Why am I not allowed to use new line? Brother. Okay, that's fine. So I imagine I do it like this. And then here, if I want to use the rand09, how do I use it? So, yeah, what do I do? I just wanna rewind. Create rand. So do I just do that? Do I just do let mute RNG be equal to rand two dots, and then like this guy, RNG, and that's it? But it's telling me that I should be using rng.random. So I imagine it's this guy, rng.random. Okay. So how do I specify you don't need the extern? Okay, what do you mean? Do I just need create? No. I'm just gonna have it like that. So the thing is, how do I generate a big integer with this RNG guy? Plus, how do I... Okay, so I want to sample from the uniform distribution. And rand09 allows us to do that, right? And so how do I... do I just do like... Oh, shoot. Okay, let's try with p. So just do let p be equal to what? Okay, let's figure it out. P would be equal to a uint. Oh, sorry, wait. It would be a uint, right? And then I do this, and then I include 1536 bits. And then I don't know what the other guy was. Limbs. What is limbs? What is limbs? Wait, I may just be stupid, but... Oh, using bits over 64. If you try to construct it with the correct arguments, ideally this would be a path error, but that's blocked for us. Okay, can I just do this? Uint 1536. Let's see. Ooh, let me see. Whoa, there's a lot of people. Whoa, hello. Artemid, are you generating an RSA key from scratch? Yes. Yes. So, as you can see in the comment, generate RSA keys. It is actually allowed to have new lines and tables, but starting from toml v 1.1.0. Brother. Okay. Flix Tech and Gaming. Yo. Very, does Rust have a type to work with big ints? No. You have to install an external package to work with big ints. It's driving me crazy. What's up, G? Hello. Okay, so let p, right? And then we do uint. Okay, so now we need to generate a random number of 1536 bits. Can I do RNG Dot random. No, I cannot do that. Okay, wait. How to generate a random big int in Rust. There you go. This guy has the same issue and we were looking at it. So it says big int be gen big int. Gen big int. But this guy is telling me that whatever they have here, which implements the standard uniform distribution sampling, is called through rng.random. So who do I believe? Who do I? What am I supposed to do? Like this guy here, the sample random bits new 256. Thread RNG. Okay, what is the difference between thread RNG and then? Yeah, why are we doing this? I had to do them from scratch and see. You're good. Wait, that's an interesting thing. So how difficult do you think that is? Because like my thing is like I don't know how excited I am to implement like big integers in Rust from scratch, not knowing anything about the language. Oh, it's okay. Let's see. RNG.random. And like, am I supposed to, brother? Okay. What am I supposed to do? So random. Oh, it just doesn't. What? Generate. No. Okay. Do I have to do this as a thread RNG? Yeah, what am I looking for here? What is this tricky business? You need to use the new big int. I know, but like arguint says it provides support for random number generation, right? You will have the gen big int. Yes, but like when I try to do that, when I try to do dot gen, right? Like it's telling me basically it doesn't exist, right? Gen big int, because that's what I imagined, right? Like since arguint is inheriting from big int, it would just let me do what the Stack Overflow post is suggesting. But like it's not auto-completing, which gives me the illusion that it just isn't it, right? Because if I do this and then I do 1536, yeah, I'm not understanding why is there no auto-completion here going on? What's happening? Okay. Cannot find type uint in the scope. So I imagine it would be uint. Oh shoot. Okay, so how do I... What? Thread RNG function is not existent. So you see, thread RNG is not there. So is it just RNG and then I can just call... Yeah, and now gen begint is not a thing. Wait, because that's exactly... If you go here and like... Wait, no, that's exactly what I did. Like, if I look for rand, and then it shows you the page that I had opened right here, showing you guys that it actually supports random. So, this is what I am confused about, right? Like, this is not search. Okay, wait, what do you mean this is not search? Like, oh, there's like a little button. Ah, I see, random. Oh, yay! Thank you. Yeah, that makes more sense. I did not know the wiki had this possibility. Let's see. Function random, standard uniform, available on create feature thread RNG only. Okay. Generate a random value using the thread local random number generator. Okay, this is the rand one. And then if I search inside the ruint one, yeah. So wait, but this explains why this was generated an error. We needed to implement this feature. That's okay. Random. Ruint random. Okay. It's random. Available on create features RAM09 and STD only. Creates a new uint with the default cryptographic random number generator. This is currently rand RNG. So am I able to specify? No. So does the function just like knows what size of uint I want and generates that from the template parameter, from the generic? Like I don't. What? Well, yeah, I imagine, right? Because it has access to it through the input. It has access to it through the input. And so if I just do, so instead of this, right, if I just do ruint, and then I specify, sorry, if I just do uint, and then I specify the 1536, sorry, okay, it's telling me cannot find type uint in the scope, not found in the scope. Use ruint uint. Yes, okay, perfect. What else? So let me just put a bogus value here, 0. Is there an error with that? Yes. So I need to give them the limbs. 1536 divided by 64, that's 24. So 24 words is what this number takes. Great. So now I do uint, I pass in the two template guys, generics, whatever the name is, and then I do random. Oh, that's so much simpler. Thank you so much, Andrew. Andrews are safer today, as usual. Maybe the fact that I don't know how to use, crates documentation, and I'm stupid and didn't realize that I could just search for it. Random. Yo, let's go. Perfect. So we have two random numbers of these many bits, and I imagine it's a uint of. Oh shoot. Okay, it doesn't change it. Okay, so it should be uint of 3072. I think it's the addition of those two, yeah. And then it's not 24. It's I imagine 48, right? Mismatched types. Oh shoot. Okay, so that means that I need to. Oh no. Okay, so how do I cast in Rust? Can I cast between these two things? Let's see. Ruint, I already have it. So here. How to cast in Rust. Casting in the Rust by example documentation. Rules for converting between integral types follow C conventions generally, except in cases where C has undefined behavior. Okay. Oh, I say as this. Okay. Oh, from and into. Oh, you're right. Wait. Yes, I remember when we were learning about this in Rustlinks. Sorry, 3072 and 48 from this guy. Can I do that? It seems like it. Yo! Okay, uint and then this 3072 over 48 from Q. Yo, let's go. Okay, so now n is a value of 3072, 48. Yo, let's go. Excellent. P dot widening in mole Q. Oh, is that a thing, right? Is that a thing? P dot widening. Ah, I see. Let's see. Calculates the complete product, self.RHS, without the possibility to overflow. The argument RHS can be any size. The result size is the sum of the bit sizes of self. So, is it just faster if I just tell it what their sizes could be? Because I imagine that the machinery between like whiting and malt is accounting for like I don't know what the other guy is, right? I don't know what the other guy is, and so if I specify them and then multiply them, I think it's better, right? I don't think it will make a difference. Okay, so let's do whitening multiplication then. Feels a little bit simpler. Whitening malt. Whitening malt. And then Q. Maybe slower to compile though. No! Okay, that's fine. Yeah. Okay, so we have that. Now we need to know the totient, but we already know what the totient is. Is p minus 1 times q minus 1. So let me just say let tot be also a uint of 3072 48, and that should be p minus 1 dot whitening malt. Hold on. With q. Can I not have subtraction? Oh, okay, I just need to convert it. Okay, this is a little bit annoying. Actually, very annoying. What? Yeah, this is not... Okay, it's fine. 30, 32, 48 from 1. No, okay. Oh, sorry, it's 1536. Okay. 1 dot into should probably work. Oh, really? 1 dot into. Type annotations needed cannot infer the type. Okay. Yeah, it seems like it's not. Yeah. Okay, I don't like this paraphernalia that have to go through just to put like a -1. That's a little bit annoying. Can I just do uint 1? Seems like I can. So let's just do that. Also, this keygen function is not reliant on runtime either, but is a const or shifted to build.rs into a keygen.rs. What? I'm not sure what you're talking about, RPC 2.0. Maybe you can explain it further? What do you mean? It's not reliant on runtime either. Does random not rely on runtime? Like what do you mean? It's a PB for later. Okay, so maybe we can finish writing this and then we can continue with that. Sorry, maybe I'm thinking too much. Okay, don't worry. Maybe I'm the one that's not thinking enough. So that's completely fine. Okay. Let's see. So we need to calculate the totient function. And so this totient function needs to be q minus uint 1. Perfect. And so now for a random e, we say let e So we need to draw a random element from this guy, from Z star, right? Drawing a random element from Z star is equivalent to drawing a random element from 0 to totient function, many numbers, right? Because that's how many you have. You have totient function many numbers. I imagine that random is random inclusive or exclusive? Like if I want to generate up to some ceiling. Because I could do let E be something that's going to take around the same amount of bits to represent as the totient, which is going to be equal to, and then generate a random number based on that. So now I need a way to have, oh shoot, this is the wrong one. So I need to find the IO integrate. I need search random. I need a way to be able to pass a sort of maximum, pass a max guy. But I just don't see it. Oh wait, min. Oh, never mind. Has limbs? No. Because it seems like we don't have a random guide that allows us to have like a ceiling for the random number. That is concerning. I know we could just do like, oh, just generate the random number and then apply modulo to it. But I think that would be certainly like prone to attacks. Like if we want to take it a little bit seriously, right? Because whatever numbers are greater than the actual thing we're looking for are gonna wrap around. So some numbers have more possibilities of being generated than others. So what do we do? Randomize, mute self. Fill this UN with the default? No. No. Invalid digit, invalid radix, space convert error. What am I supposed to do? Overflowing how? No. Okay. Function random. Generate random argument with bounds in Rust. Yeah, how can I generate a random number within a range in Rust? Oh, no, but I want the big integer. Okay, maybe we can try to guess. uint, and then 3072, 48, and then like gen something? No. There's the dots. Ran. Yeah, no. I don't know what to do. Using gen range. Yeah, so the thread RNG would allow us to do it. It seems like this one doesn't. 1536 code 24. Random. Creates a new UNT with a given random number generation. Fills this with the default cryptographic. Randomize width. Fills this with UNT. You know. Do I have something like RNG? No. So maybe this, and then I can generate an RNG over here. Something like let RNG, mutable RNG, be equal to rand, and then RNG, RNG, I can use a dot gen range. No, okay. So let me look here in random. The red RNG is a feature maybe that I need to put in. So version equals this. And then I say features. And that's equal to thread RNG. And then maybe I'll be able to do this. So if I do this and then I say thread, no. Okay, RNG dot, no, range. Random range, there you go. Random value in the given range. Okay. So we make it follow whatever's going on here. I am not sure if they have support for big integers. Guess there's only one way to know. So if I say uint 3072 from 54, what's that? 64? 48? 48? Then I say from, and then say from 0 all the way, well, I guess there's no 0. So from 1 to uint 3072, 48, and then I specify 10, just to test it. Yeah, no. Oh my god. What is this? What is this? What is this? Like, how do we even... Okay, this is peak rage rate. I don't know how else to describe it. Like, it's supposed to be a simple task, buddy. Wait. Random range for big numbers in Rust. Are you in it? It's not that difficult. Please. Please. Rand begin. Okay. I don't think it's implemented here, though. So yeah. Anything I do is this is so bad. So what do I diff seal for BE bytes? And the library doesn't provide that method, right? Because uint, yeah, if I look for random inside the library or rand, it just completely gives up. So ruint search rand. the same methods as before. Maybe this guy can save us? Oh no. Never mind. Okay. Search for RNG. Oh, it's sorry. RNG? No. Can I do range? No. Okay. Ugh, this is frustrating. How do I even work this? He is just a random guy. He just needs something that falls in between push and push. Because another thing we could do is just say like, while the value falls out of the totient, just ignore it. Do I want to do that? I am not sure. But like, it just seems like the thing we need to do. Right? Do something like this is equal to while, and then this guy here. Like while, I don't know, the random value we generate while e is greater than the totient, just like generate it again, right? E is equal to u int 3072, 48, blah blah, argument, what? Oh, sorry. And then I say random, right? So it's like, how am I supposed to continue? Cannot assign twice to mutable. Okay, yeah, sure. Let's mutable e. So I just do this. Do we have a do while here? And like, here, do this while we continue to do that. No. Seems like we don't have that. Oh shit. Do while, rest. Does not have a native do while. Okay. Never mind. To keep the language simpler. Bruh, you already introduced like thousands of complex things. Why can't you have a do while? Okay, that's funny. 37 and 48, and then random again. Yeah. Greater or equal to the totient function, because totient is 0. Yeah, so I think this is the way we're gonna have to do it. Honestly, I'm like kind of tired of looking for a way to do it in the first place. Great. Okay. So we have this, right? We have E. Now we need to compute D. So it's gonna be the other guy. So well, actually, I think like, yeah, not only that, but we need like Well, E is greater or equal to that, and on top of it, their GCD, right? I think argument includes a GCD. No. Okay. Well, E dot GCD of sorts. Yes. Okay. E dot GCD between him and Todd is, or E dot GCD between Todd is different from 1, then we need to continue. Right? So, yeah. What does this function return? Returns itself. Okay, are you in? Alright. And so we just keep generating until we find something that has a GCD of 1 with tot. Once that's done, then we know that it has an inverse. And we actually would be able to sort of simplify things by using the extended GCD, if I remember correctly. So let's mute x GCD. So what does this guy return? So E dot extended GCD extended with tot. What does it return? It returns self, 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 and bool. Okay. It's unstable and may change in a minor release. Yeah, don't worry. Why sign such that okay. Returns math x and then fdty. So it just returns the zoo coefficients of our extended GCD, just like we planned before here. So you remember that we have extended GCD, right? And with it, we're able to compute the inverse. I wonder what it is. There you go, extended GCD. And it returns this guy, and this guy. So if d is equal to 1, then this is multiplicative inverse of A, otherwise it has no multiplicative inverse, yeah. So D would be the divisor, right, the GCD. T would be the first Bezout coefficient, S would be the second. Sorry, this parameter would be the second Bezout coefficient. Let's see. Yeah, return S. So S would be the multiplicative inverse of this guy. Okay. But that does not seem to be the Bezout coefficients, yes. Returns the GCD, X, Y, and sine. X being the first Bezout coefficient, and I think in the paper we talk about, yes, S as the first Bezout coefficient. Perfect. So that means that we can just do something like this, where I say ds and then some guy I don't care about. Is this possible? Mute must be attached to each individual. Okay. Actually, none of them should be. Yeah. Mismatch types, expected tuple of this thing, bool, found tuple. Okay. So I'm not going to use those last values, right? It seems like it to me. So then I say, while this happens, or D is different from 1, then continue and continue and continue doing this until you find what it is supposed to be. So can I do DS nothing, nothing, nothing? So something like mute, 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 mute. By a named binding. Okay, so I'm just gonna call it T, and then I'm gonna call this one like something else. I don't know. I. There you go. Okay, this guy is gonna be equal to. Well, actually, let's name them useless and double useless. Great. Perfect. And these are going to be e.gcd extended with the tertiary function. Yes, perfect. And so now what we can do is once we're done, we're going to be able to know what the inverse is. Right? So I guess we can start applying some of the knowledge that we acquired from Rustlings maybe? And we can start saying something maybe like math. I wonder if that's possible. Actually no, let's not do that. Let's just keep it simple. So we have while this happens, GCD extended. Actually, I do think we're gonna have to use a bunch of inverses. So let me just do something like math. Can I do that? Math.rs. And then here inside of math, I can create a little module. Right. Let me think. I don't think I need this. I think I just need math. And then I can just say inverse, something like that. No, I don't think so. It's okay, it's okay, it's okay. So let D is actually a very bad name. So GCD, then GCD here, then GCD here. Perfect. So now let D equal to S. I guess we can just make it be flat from the beginning because this D is going to be a private key. Perfect. So now we have everything. Because computing inverses. Yes. Perfect. Perfect, perfect, perfect. Yes, that's fine. So here, we make D be equal to the inverse of that, but we already have it. So now the only thing we need to return is all of them. So we need to return N, E, and B. Great. And what we return, it's going to be a uint, well, it's a uint of, N is 3072, of course 48. Let me just check that. 3072 divided by 64, yes, 48. Oh, sorry. Alright. Great. PQ random, NED. Yes. Okay. So there's that guy. Then the next guy, which is going to be the E and then D, all of them are going to be 3072. Yay! Alright, we did it. Maybe what? Maybe it is overwritten before being read. Yeah, but I wanna... Okay, so it seems like I can just attach this. 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 How? Okay, can I ignore fields in the tuple dereference? Let's see. Ignore fields in tuple dereferencing Rust. Oh, I see. Wait, that's pretty cool. So then I can just do this. right? And then I can just do this. Oh, perfect. Yay, let's go. Alright. Awesome. Wait, it's our first Rust function. Yo. Alright. We got it. Yay. Okay. So we have keygen now. I just want to see what happens if you print stuff, like, you know. What happens if I just say print rsa.keygen and then I just show whatever it returns. So how do you format stuff in Rust? Do you just append everything? So if I just say let n end be equal to crypto encdec, right? Oh shoot, crypto. What? Crypto encdec, yeah, encdec. Wait, okay, there seems to be an error of sorts. Encdec. Then it should be able to let me do RSA, right? I'm gonna delete this line because it's causing problems. RSA and then keygen. Module encdec is private. Oh. Oh, wait. I forgot to do that. Yeah, my bad. Poly module RSA, yes. Perfect. So if I do crypto now, yeah, now it works. Okay, perfect. That's all. RSA. And then here keygen. Yo! Okay, can we print them? Println. Then do something like RSA dot keygen. How to print things in Rust. I don't know how to put the values inside. Yeah, formatted print. So it is the same as C, basically. Seems like it. Okay. So I imagine that there's some sort of trait that allows me to print these numbers. I'll just hope. Seems like it. Great. Okay, so now how do we compile this project? I think it's a cargo something, right? Rust C. Okay, so then I say Rust C, Rust compile, main.rs. Couldn't read main.rs. Oh, is it src/main.rs? Cannot find crate. What? Okay. Oh my god, what's going on? Cargo build. Oh, okay. Cargo build. Ah. Thank you, RPC 2.0. Perfect. And then cargo run. Yo! Look at that. What? Hey! Hey! Okay. Okay, wait, this is great. And then, like, verify. So one thing we want to verify is make sure that, like, the multiplication of these two guys, mult, is actually the thing it's supposed to be. So E times, what's the name? E dot mult, I think it's like, how can I, mod? Yeah, multiply mod something. Yes, D, and the modulus would be the toe. Ooh, but then we cannot know the totient. Are there asserts in Rust? Can I have something like an assert? Then if you want cargo build release, release builds faster, usually drawn later. Ah, I see. I see. Thank you. So here, do I have asserts in Rust? So something like assert? Yes, it seems like it. You can change the profiling cargo that's multiple. Okay, perfect. Thank you. So let's see. Assert something. So what I want to assert is that e dot modulo multiplication. Sorry. Multiplication mod. Yeah. D with the modulus being the totient is equal to 1. So that's the thing we want to assert, just to know, right? Cargo build. Oh shoot. Oh, that's because I have more than I should. Cargo build. Yay, and then cargo run. Oh damn, no assert. That means it worked. Let's go! Okay, we have our keygen, our RSA keygen. Wait, okay. This is great. This is great, 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 great. Okay, so we have solved all of these issues. How to draw a random number in Rust, we know that. How will we discover the elements of this guy? Well, we simply go in a while loop. How to handle huge numbers? Fine. Yay! Okay, perfect. This is amazing. This is amazing. Perfect. Alright, we have our keygen. Yay! Okay, so what do we do now? Seems like our next step would be to write the encrypt function, right? We need to encrypt something. So if we need to encrypt something, right, that something better be some kind of payload, some kind of, you know, little guy or whatever. So let me transport this to the third workspace, and then we can read again. Great. We have the RSA assumption, yes. We have the KEM, but we don't really want this. Yeah, what we want is, let's see. So the message can live inside of ZN, which means we're gonna have to partition the message every single time. That's fine with us. Let's see. Encryption of this with the PK is just raising it to the power of E, and decryption is raising it to the power of D. As we saw, this is not secure because you're able to have sort of chosen ciphertext attacks, if I remember correctly, or which one was it? Where you're able to just encode your guess of what the message is and then compare it to the actual ciphertext. So this is not randomized. How do we perform RSA encryption so that it is secure? So it seems like, let's see, can we remember what it was? Let's think. So we need to draw some sort of random value and be able to somehow solve the algorithm. Yeah, this is the KEM. We don't really care about it. The Chinese remainder theorem we saw already. Yes. Yes. And so, sorry. Oh, wait, we're not provided. Okay. Okay, so this is a modification to allow for KN, but how can we make RSA encryption secure? Let's think about it. Because it means we need to somehow randomize the ciphertext and be able to allow the other person to just oh wait, couldn't we just do something like this? So if we wanted to make it like secure and I don't know if this is secure, but this is my proposal. How about when we go and encrypt whatever we're looking at, right? So it's gonna be C is equal to M, right? Instead of doing, so it's currently M to the E modulo, I think it's N, yeah, modulo N. Instead of doing that, we draw some random value, right? From, okay, so currently M belongs inside of, what was it? Yeah, Zn. So better yet, curly M is equal to Zn. So I propose would be something like having R be like some, let's think. Because what I was saying was like, oh, draw R from Z of n over 2, assuming n is even, right? And then your encryption is going to be the original message. So now the message cannot be drawn from Zn, it has to be from Zn over 2. And then your thing has to be M attached to the random value, and that to the power of E modulo n. And so each of these is n over 2 bits. When we combine them together, that's n bits. And then the power of E. Great. Then this makes the ciphertext be random and makes it sort of be able to resist the attacks we've seen so far. And this would be encryption, right? And then during decryption, what we can do is we can simply decode it. So it's like, D is equal to whatever you gave me, which would be the ciphertext, and then the private key, like secret key or whatever, all of that. I just do C to the power of, I think it's better if I change them, yeah. So whenever I decode this, I'm gonna obtain M and R. C to the power of D mod N. And then that's it, and then you just return M. Return M. Right? This would protect us from the insecurities of textbook RSA. This seems about right? Feels to me. Yay. Okay. So if nobody opposes, I think we'll be more than fine. So encrypt. To encrypt, we need the public key, right? I guess it's better if we just name them PK and SK from the beginning. So this is public key. This is the secret key. This is the public key. This is the secret key. Well, they're not necessarily the public key and secret key, so never mind. Because the public key is, I guess, like both N and E, so that we know how to play with them in context. It's fine. Okay. So PK is just a tuple of two values. One of them would be a UN307248, and the same for the other one. 307248. Perfect. That's PK. And then the ciphertext no, sorry, the plain text, which would be sort of text, right? Like p text, would have to be a number too, right? We just require the user to give us the input in the form of a number. There could be another way to do this where we just ask them to pass us a string and then we convert the string to a number and so on and so on. Let's do the simple one where we just encrypt with, assuming that we're already in the number. So what we can do is we can grab R, right? So I'm going to say let R be equal to uint of. Okay, so now we need to decide, right, how long things are going to be. Okay, so Zn. So how many bits are you gonna use for this? Okay, because by what I mentioned, right, which is, I'm going to bring it to this workspace, yeah. By what I mentioned here in the Excalibur, right, we're going to have like z, right, z n over 2. So it depends on what the value of n contains. I think if I just do let n e be equal to pk, right? Then I can do let R be equal to, it's not units, it's units. But what I want is to grab a random number in the Zn over 2 sort of like space. But this once again creates a problem, which is we cannot have random with range. I hate this so much. Okay, let a uint uint 1536, which would imply 24 limbs. So while R, so R is just gonna be equal to a uint 1536, 24 random guy. So random. Wait, what? Oh. Rand, and then this guy here. Random. Right. Then while R is bigger or equal to n, we're going to continue generating. R be the same as uint of 1536, 24. I guess I don't need to specify that. Of course I need to make R mutable. And then U would be equal to a uint 1536, 24. Blah 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 blah. Random. Okay, and then here, instead of n, it should be n over 2. Cannot divide this uint. Oh my god. Okay, division. Can I do division? Wrapping division, strict division. Okay, what are the differences between each of these? Panics if the right hand side is equal to 0. Compute self, rounding down. Checked division computes this guy, returning none if this happens. Strict division computes this guy. Oh, I see. So the difference is in the panics. Okay. So what? How do I do this? Because what we need to do is say R is greater or equal to n dot divide. So it's n over 2 that we want, right? So we need to guarantee that n is an even number? No. Okay, I'm just gonna do it rounding down. Wrapping division. With 2. That's it. 2 to n 2. Can I do that? No. The trade bound un from integer is not satisfied. What? Okay. So then I need to do un blah 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 3072, 48 blah blah from the 2. Oh my god. Can I just do uint 2? Is that a thing? No. Okay, well. Greater or equal to that. And it seems like we can't compare these two together. Okay. Can I do something like greater than? No. Okay. It seems like I need to convert them first. So this guy needs to go to a 3072 48 from this thing. That's it. Perfect. It says unnecessary parentheses. I don't believe the parentheses are more than necessary, but that's okay. R would be equal to this little integer guy. We pick a random number. Yeah, no, this is not. Oh, let me think. Actually, no, yeah, that's not possible. Yeah, let's just make R be around 36 to 48. Right? Because R needs to be, yeah, R needs to be of this type. 7248, so never mind. I was the one that was wrong. This thing is not a 1536, this thing is 3072 still. 48. So there's no need to convert it. Yeah, okay, perfect. So we just generate random numbers until we get one that falls inside of Zn over 2. And that's sort of it. Right? Yeah, and then what we do is... Oh no. We need the p-text. Actually, okay. What? Wait, give me a second. Dude, what am I doing? What am I doing? What am I doing? Yeah, this makes no sense. I'm just like very stupid. This is fine, right? This guy is not fine. This is also not fine. Right? We can just compute that random number if I am not mistaken. This is... Good morning, Valley. How are you? We're here writing in Rust, our cryptography library. We already created the keygen for RSA, and now we're doing again. So we're trying to implement encryption. Dude, this would have been so much easier in C++. Wait. Okay, let's see. What do we need? So currently we say while r is greater or equal to something, R is equal. I've been experimenting with coding new inline assembling. It's really cool. Yo, what is it? Yeah, let's see. While R is greater or equal to something, R is equal to the uint and then it's random. Yeah, oh it is, yeah. But it's uint. Oh no. Okay, I think so. Is n is not guaranteed to be. That's my problem. Okay, so what is it that I'm complaining about? What I'm complaining about is the fact that whenever we want to encrypt something, it depends on the length of n, right? On the length of n. And so currently what we need, it's like, suppose that for some like impossible odds, right, we somehow managed to draw p being equal to 2 and q being equal to 3. The most breakable ever RSA thing possible. And then our n would be equal to 6. What this means is that n is like 3 bits long, right? Like only 3 bits are necessary to work with it. So to represent an element in z's of n, we need only 3 bits, which means that our message can only be 3 bits long. So that's annoying. But suppose that the user gives us a 3-bit message. Then, because of the thing that we're appending, which is this little guy r, because of this, right, we need to separate at least a given amount of the bits to go for the random value. And so, what should that amount of bits be? That's the first thing. And then the second thing is, how do we determine the amount of bits at n is? Because this was supposed to be like, a 1532-bit number, and this was supposed to be a 1532-bit number. But I cannot just generate a 1532-bit number and attach it here, right? Because that's just not the way it works. I need to generate that random number based on the minimal amount of bits that are necessary to represent n, and even then, I wouldn't be able to do things like this. So, like, what do I do? What do I do? What am I supposed to do? Maybe the method of attaching is not adequate? I'm so confused. I hate this so much. Okay. Can we divide it by 2? No. Can we ignore the last bit? No. Dude, what do we do? Well, r is greater or equal to this guy. R is equal to this random thing. Does anybody have an idea of how we can tackle this? Because I don't. So I could choose a random value and then like add it to whatever we currently have, but that makes no sense. Use it in the exponent, but that doesn't also make sense. Okay. Yeah, the only way I can think of protecting against the mentioned attacks is by doing this. Is there a different way to do it? Maybe that doesn't involve attaching something and then we don't even know what we attached and then everything is just bad. Hmm. Dun, 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 dun. Is this salting? Yes and no. Like, I am basically trying to. So, there's a problem with RSA sort of textbook encryption, which we can see here. Textbook RSA encryption, right? Textbook RSA involves grabbing the plaintext, raising it to the ETH power, and then returning the ciphertext. And then when you want to decrypt, just raise it to the D power. The problem is that this is insecure, surprisingly. The reason is because you're prone to somebody saying, I want to guess what the plaintext is. So they try to guess, and then they encrypt it. And since encryption, this encryption algorithm is deterministic, they can get the same ciphertext as you. So they can know what you encrypted by trying to guess what it is. Right? And so it says it here. This is not secure. The main reason is quite obvious. It's deterministic. An adversary who has a guess of the plaintext value can check whether that guess is true by re-encrypting it. So never use textbook RSA. And so later, the author just continues and continues, but never gives us sort of a solution to the RSA encryption protocol per se. It gives us a KEM, right, which is nice and all, but it doesn't give us a solution to this. And so I was thinking of a solution, and the solution I honestly think is possible is this one, right? Draw a random element, not from Zn over 2. Ignore this. This is like just completely bogus. Just grab a random element from half the bits of n. Okay? So if n is 10 bits, grab a random 5-bit element. Then your plaintext is only allowed to be 5 bits. And so to your plaintext, you attach the random thing. And then you encrypt. Now, when you encrypt, you see that the C is random. Right? And like, you're not going to be able to sort of guess or see what it is. Then when you decrypt, you just raise it to the power of D. You know that the last few bits are just bogus, so you ignore them and just return the first 5. So that's sort of my idea. I'm not sure if it is secure. It's like, it's a little bit better, right? But completely secure? Well, I'd say yeah, right? Like, yeah. It seems intuitive to me that it would be secure. M could be any sort of message. R could be any sort of, is any sort of thing. There's no way to extract information from it. Yeah, seems fine. And so yeah, I don't. So now the problem becomes like, okay, right? Like, how do I know the amount of bits that it occupies? How can I make my message have the amount of bits that it's supposed to have? Like, that's what's sort of tricking me right now. Oh shoot. Sorry. My earbuds fell to the floor. There we go. Alright. So, yeah, so M, let me attach R. E, and then you return N. Because here where we are, right? First of all, like, you don't know how many bits n is. Like, n is at most a 3072-bit integer. But it could just be, as we see here in the example, 6, which only requires 3 bits to represent it. And so you only have a possibility of like 6 possible messages you can send. So you need to figure that out and then generate an R that it's adequate for it. And so, yeah, it just... I don't know. So how to know the amount of bits necessary to represent a given number? Is that something we can know? We can take like the log base 2, of course, and that would give us sort of the lower bound on what it's supposed to be. So log 2 of 2 is of course 1. Log 2 of 3 is like 1 point something. And so if we seal it, then we know the amount of bits that we're going to need. I mean, because log base 2 of 7 is like 2 point something, 2.8. Okay, so we can just compute the logarithm, get the amount of bits that n represents, and then we run. Okay. Yeah, guys, I'm like very stuck on this. I'm not sure what to do. You could just append random bytes to the end of the plaintext before interpreting the plaintext as a number, no? But like, you still need the plaintext. Like, that doesn't get rid of the problem, right? Because you still need the plaintext to be within the confines of n. So the plaintext is an element of z sub n. Right? So if you need to add the random bytes, then like, and in fact, like, that's exactly what we're doing, right? Like, we're just adding r to the plaintext, but like, you need it to live here inside of zn. And so before you give me the plaintext, you're gonna have to do the same process. You're gonna have to figure out what are the bits that, like, how many bits it has, and so on and so on and so on. Is RSA block based? I am not sure. I imagine it is, like, right? It's the only thing that makes sense because, like, you can only draw your elements from here. So you have to just you have to partition the message. If it's a very long message, and send it by little pieces. But yeah, so, although I'm not sure if block-based means something else in cryptography, but yeah, so you still need to perform the same procedure is my problem. So we don't get rid of the problem at all. So how do we solve this? If we get to know the amount of internet, because I mean, z sub n, right? Z sub n has n many elements. And so to pinpoint what an element is, we just need, right, however many bits you need to represent n. And actually we cannot use all of those bits, because if we do, then we may end up with things that are out of bounds. We don't want that. So an example, right? Like if I tell you, oh, we need to have like, right, n is equal to, say, I don't know, n is equal to 8, right? 8. Well, no, 8 is a power of 2, so never mind. N is equal to 6. No, actually, to 5. To 5. N is equal to... No, because that's not a composite number. 6, right? Then what happens is you're going to have 3 bits, right? Because n can be represented with at least 3 bits. So those are the bits you have available. And the thing is, you can just discover this amount of bits and say, okay, I'll designate 2 bits for the message, 1 bit for the random thing. The problem with that is it's not like you can use all the bits, right? Because n is equal to 6, so a message like this, 111, which is 7, is like completely out of bounds. It's not even an element of Zn. And so you also have to protect yourself against that. So not only do you have to extract the amount of bits and dedicate like these bits to this thing and these bits to the random thing, but you have to make sure that like whatever is being output like falls within n, right? And so it just doesn't, I don't know, it's like kind of frustrating. Then it's like, I don't know. Or we could just do textbook RSA, not worry about it, and then look at it later, but it's just not. How is the n in Zn decided? The n is decided from the key generation. So when you generate the key, you grab 2 random primes of 1536 bits, and then just multiply them together, and that's your n, right? So it's possible that this prime is a huge number. It's also possible it's 2, and that this one's 3, and that n is now 6. Like, and so it's you know, it's a little bit complicated. Because yeah, nothing works. Nothing works. So let me think. I thought the primes had to be large. I mean, not necessarily, right? Like, they are most likely large, but not necessarily. And like, it's better when they are very large, but you draw them randomly. So I, like, from what I understand, right? In fact, the algorithm itself, like, the book itself tells you, like, oh, these have to be like uniformly choose k over 2 bit prime p and k over 2 bit prime q. And their Sage code also shows you that it just says, where is it? Random prime, and the ceiling is 21536. So it could be 2, or it could be 3, right? It just feels like you shouldn't have to give special consideration. No. I'm not giving them special consideration to being small. I'm just using small numbers because it's easier to think about. I'm just showing the fact that like if you want to append stuff, it like becomes tricky because it could just be the case that whatever you generate ends up being an element that's outside of Zn. But I think I have a solution. So what I'm thinking about is if you have a thing. So I think this may just make us implement the thing with like arbitrary large numbers. Like okay, we can just have something like this, right? You have your plain text, you add to it the random bits or whatever, right? Independent of what they are, I honestly don't care. And this is going to be a huge message. Huge message. Then what we do is we modulo by whatever n is, and that number is of course going to fit within Zn. That is already a member of Zn. And that's exactly what we send. We repeat this procedure by subtracting whatever the modulo n was. We subtract from it, and then we go again, modulo n. And then we send that. And then we subtract this, and then modulo n. And then we subtract this and continue. Then modulo n. Then we subtract this and continue, and continue, and so on, right? And so that way maybe we can do it, although this randomness was attached just so that we could, like, this randomness is not intended to be attached to the entire plaintext. It's intended to be attached to every package, right? Because it's involved in the encryption-decryption process over here, as we already know. And if we don't do it this way for every package, then it's sort of useless, right? Because we're just gonna end up running out of all the things we added here, and then eventually it'll just continue doing that process but for M. So we still need to add those random bits at the end for every package, so never mind. If n is like a budget, okay, wait. Yeah. If it is like a budget per block, you could just allocate some fixed part of each block's budget for randomness. Yes, that's exactly what I'm trying to do. Like that's exactly what I'm trying to do. That's why I'm saying like, oh, right, M is drawn from like half many bits as n, and then the other half of the bits are used for R, right, the randomness. But I'm saying that doesn't work. Like here I was saying, dedicate these two bits to M, right? And then dedicate this last bit to randomness. And it doesn't work because like you could have this very specific scenario where like M lives where it's supposed to be. M is small, right? In this case, M would be 3. And then the random bit happened to be 1. And so now the element you're trying to send is the element like 4 plus 2 plus 1, which is 7. But the number 7 doesn't belong inside of Z6, right? It's just completely out of bounds. And so you need to restrict it so that it like, you know, it fits within what it's supposed to. You could say just ignore the most significant bit of whatever the number of bits that it has is. I would say, sure. The problem is I think that would be insecure too, right? Because then, like you have just reduced the amount of elements from which the plaintext is being chosen. And so, like, I would have to think about it more deeply, right? But it just feels like it's not, right? You're not using the total space of Z sub n. You're using only a subset. And so an attacker could just benefit from that. But you can arbit. Oh, sorry. I clicked the pin. Wait. Sorry, how do I unpin this? Unpin this message. There you go. Sorry. But you can arbitrarily chop up M to fit. Yes, I am indeed I'm in fact assuming that M fits, right? Like here I'm saying M fits in 2 bits. But that's not, also the randomness should be fixed to length, even if you generate a small number, that could fit in fewer bits. Yes, I agree. Like the randomness is fixed length, like I never said it was not fixed length. That's why I say, like, we're gonna dedicate these last few bits to randomness. That means all of those last few bits. The problem is what I'm illustrating. Like, you could end up with elements that just are out of bounds of z's of n. Like this example with 7 illustrates it, where the random bit is 1, the plaintext is just this guy, 1 1, and then you have 7 as your total thing to send, but 7 is not inside of zn, right? And so it doesn't matter if you chop up m, because then each piece of m, we need to perform this procedure, right? We need to perform this procedure to each piece of m so that it's not possible to guess what's going on. And so this problem is just equivalent to thinking that m already fits, just like it does here. So yeah, that's my problem. Like, I don't see it. Because let's see. The problem is, in your example, is that you allocated 3 bits for an n of 6. Yes. Like, okay, so are you suggesting just using these 2? So then you're not using z's of n. So if n is 6, right, these 2 are not going to be enough. So then you would have to pick a different n. And if you pick a different n, then the problem again resurfaces. Right? Because like this is equivalent to just not using this bit over here, which means you're using less elements than the entire space of Zn, which could be prone to attacks, because now the attacker knows, oh, this person only uses the first half of the elements. Is my thing. Right, so if n is 6 and I'm using only 2 bits, it means that I can only send a message that's like 0, 1, 2, or 3. And the rest are just unused. So an attacker is going to benefit from saying, oh yeah, this guy just uses the first half. That's a different problem than padding with randomness. What? What do you mean? Not really, because I can control what the person gives me, right? I can say, whatever this is, it better be an element of Zn, and then we're just happy, right? But when you include the randomness padding, right, you need to account for the fact that whatever, like, when you do things, you could end up out of bounds. That's my problem. Like, if we didn't have to pad with randomness, then I could perfectly say, make the plaintext just be, an element of Zn, and I don't care how you do it or when, but as long as that thing fits inside of Zn, I'm happy. With the randomness, it's very possible that, like, since you dedicate a fixed amount of bits, right, there's, like, not all the possible values of that fixed amount of bits are possible. So then you need to do your randomness, but, like, constrained. Right? And that's the thing that annoys me. Because I'm like, dude, like, right? So, how? Give me a second, I'll be back. Hello again. Um. Uh. Oh, I see. You're currently giving the job of dividing up the plain text evenly towards the end to the call. Yes, yes. Just to simplify things, right? Because if we are able to assume that, right, then the function becomes easier, and then we can create like a different function that is in charge of splitting things up, right? Um, so yeah, this problem just comes from already assuming that m fits inside. You could re-roll any keys with too small of n and then allocate a fixed portion of n for yourself. Then just lie to the caller and say that n is n and then your fixed amount. That way you could keep things similar. So you could re-roll any keys with too small of n for yourself. And just lie to the caller and say that n is this is still I think there's still a problem with this because like so the problem I have is not that n is small, right? This problem also occurs when n is big. Right? Like this is just a universal problem. I'm using the small values for the purpose of illustration. And it's the fact that like we have the prohibitive values that we can hit with, and randomness could take us there. Yeah, I don't see how to solve this. So, what is the problem? That way, the value the caller gives you plus your fixed amount would fill the value space perfectly, assuming the caller did their job. I think. My problem is it doesn't. I think it doesn't. Because you would have like what's the name? So here with the example of 6, right? If we trick the caller, if we tell them, right, instead of n being 6, I'm gonna tell you that n is just like 3, so that you give me values that only fit within 2 bits. That's still bad, right? Because, you know, we sort of haven't gotten rid of the problem. We still could have the scenario where they give me 1, 1, and then the random bit is 1, and then this is 7, and it's out of bounds. I could lie to them and be extremely conservative, and instead of saying that m can have 2 bits, say that it can only have 1, right? And then whatever value is generated, it's going to be within bounds. The problem that now we're not using this last bit just because of being conservative, and so now we're prone to an attack where the attacker says, oh, this guy is only using 1/2 of the space that's available to them. So it's like both ways just lead to a bad outcome. So that's what that's what pisses me off. Nikit ECC, hello, welcome to chat. We're taking a look at the RSA and we're trying to figure out sort of a couple of things here. Right, but I hope I made my point understood. Because I don't know, I'm very bad at explaining what I'm thinking. My method is still biased. I just realized since the somewhat favored the center. Yeah, something like that. So it's a problem. Yeah, I don't know. What do we do? Well, no idea. You should look into arithmetic coding if you are concerned about quantizing to a fixed amount of bits. What do you mean? What is arithmetic coding? Arithmetic coding. Separate whole bit codes to individual its characters, inputs and entire message into a single fractional number. Oh, this is. Okay, so is arithmetic coding like is Hoffman encoding a form of arithmetic coding? Charles Bloom has some really good articles on arithmetic coders. My problem is like, I don't think it would need to be like this involved. Right? I think there's just a much simpler way to do things, but I don't see how or why. Like, oh, it differs from other forms of entropy encoding in that rather than separating the input into component symbols and replacing each with a code, encodes the entire message into a single number. Is what you use if you want to encode numbers in non-power of 2 bases. Ah, that is very useful. That sounds very useful. Well, it says here, at a very broad level, arithmetic coding works by taking a character and assigning it a frequency to a table. That seems like Hoffman coding, but okay, it seems like that person got it wrong. Let's see, relationship to entropy. Arithmetic coding achieves compression by subdividing the interval 0, 1 into subintervals proportional to symbol probabilities. Never mind, it's very similar. When symbol probabilities are unequal, more probable symbols receive larger subintervals, which require fewer bits to specify a point within. This is Hoffman, though. The theoretical limit of this compression is given by the entropy of the source, which Shannon's source coding theorem establishes as the minimum average number of bits per symbol that any lossless method can achieve. Arithmetic coding approaches this more closely. Okay. The entropy reaches its maximum, yes. No compression is possible. For example, a string of independent pair coin flips. Yes. Similarly, independent ternary symbols with equal probabilities have entropy of about 1.585 bits per symbol. Compression becomes... yes. Yes. Implementation details and examples. It's very elegant, yeah, okay. But it sounds to me like Hoffman coding. Yeah. Which did you represent the symbol? For example, the sequence could just become this. Binary number. Hoffman encoding is very binary though. Yeah, but I mean, in the end, you have to convert it back to, to but yeah. Doesn't inflate seeing a new byte with making a new decision. Okay, I see. But let me... oh wait, it's already 2 p.m. I think I have to go. But... I need to keep thinking about this then. It becomes like very annoying. It's fine, it's fine. Alright, yeah. I gotta go now because it's 2 p.m. It's actually 2:04 p.m. where I am. And so, I think it's time to go because I need to do some things. But, yeah. So, yeah, I'm going to finish the stream now. And I'll see you guys tomorrow probably. But yeah. Bye bye. Hey.